Hello and welcome to section 2 of this Unreal Blueprint course. I hope you had fun learning and building the game Marble Run in section 1. In this section, we're going to be kicking it up a gear by building a new game that I have titled Crystal Cavern. We're really going to start getting to the meat of Blueprint by working with Blueprint classes, variables and functions, Unreal motion graphics and more. In this lesson, we're going to create a Blueprint project for our game Crystal Cavern. We're going to create an empty level, and then we're going to set the default level to open for the editor and also for when we package our game. So to get started with creating our blueprint project for the game Crystal Cavern, we first need to come to the Epic Games launcher. We want to make sure we're inside the Unreal Engine section of the launcher. In the first section of this course, we downloaded and installed Unreal Engine 4.20, and we're going to continue using this version of the engine. So to launch this, we can see when we're on the Unreal Engine section of the Epic Games launcher, we can see in the top right we have the big launch button, so we can just launch the engine here. Now if it's showing a different engine version, you can drop down this arrow next to this and you can select your 4.20 installation that you downloaded in the first section. So when you're ready, go ahead and click the launch. I'm going to minimize this and we're going to see a splash screen pop up in a second, and it's going to boot us into the Unreal Project browser. Now we want to go ahead and switch over to the new project tab. We're going to create a blueprint project, so we're going to leave it on this blueprint template tab here, and we want to start with a blank template. We're going to leave it on desktop or console for the target hardware, maximum quality, and we want to make sure that we do include the starter content because we're going to be using this to build our game. We can find a directory on our machine where we want to create the project to. I'm happy with mine under D/Unreal Projects. I'm just going to name my project here. Using the camel case naming convention, we can name this Crystal Cavern. And when you're ready, you can just hit Create Project. It will close down and it will start launching the editor with our project. So the editor's launched and we can now see that it's booted us into the minimal default level. So this is set up by default to launch when we either launch a packaged game or launch the editor. So we want to take a look at fixing this with our own level. First, we need to create the level. So we're going to come up to File and then New Level. And here we can choose a template for the level. We used default in section 1, but we're going to use empty level for this section of the course. So the empty level has no actors in it at all, and we can see this in the world outliner that the level is built up out of completely nothing. So right now I have a challenge for you. I want you to save your level. Using what you've remembered from section 1, I want you to save your level, and then I also want you to set the editor and game default level to your own level. And a hint here, you want to be looking in the project settings to do this. So pause the video here and give it a go, and when you're ready, come back to the lesson. So to achieve this, we first want to save the level. We can do this by coming up to File and then Save Current or Save Current As. So we can click one of these, and now it's going to bring up this Save Level As window where we have the content folder here. We can right click on this and we can come to New Folder. We can just name this something like Levels, and then we can name the level that we want to go inside of this folder here. I'm just going to name mine Level 1, and we can hit Save. Okay, so we can see in the content browser, it's now added this new folder, and here is our Level 1 that we are currently in here. So how do we set this as the default level? Well, we can come up to Edit, and then Project Settings, and then we can come to the Maps and Mode section here, and we can just drop down the Editor Startup Map and the game defaults map here, and we can choose our level 1 that we've created. Okay, so this is a good endpoint for this lesson. We now have a new blueprint project with a blank empty level ready for us to start developing our game Crystal Cavern in. So in the next lesson, we're going to start blocking out our level and also taking a look at lighting. So when you're ready, I'll see you in the next lesson. Hey, welcome back to lesson 2 of section 2, which is level blockout and lighting. In this lesson, we're going to take a look at different viewport view modes. We're going to start blocking out a level. We're also going to take a look at how we can add lights to our level. And regarding lighting, we're going to take a look at the difference between pre-computed or dynamic lighting. And we also want to disable a default post-process effect known as auto exposure or eye adaptation. So let's get started with our level blockout. We're going to make use of the BSP geometry tools that we used in section 1. And we can find these on the modes panel underneath the geometry section. So we have all these different shapes, and we can choose if we're working with additive or subtractive brush shapes. We're going to leave it on additive, and we're going to just go ahead and drag out a box. Now let's take a look at what happens here. So I've dragged out a box, but we can't really see it. We see its outline, but we don't see the box. You might see it like this, or you might just have it blacked out like this. Okay, so the reason for this is because we don't have any other actors in our level. The default level has a skybox and a directional light that casts the light for us, the sunlight basically. But we don't have any lights in our level. So we need another way of working without having to rely on lights. Well, we can do this easily by changing the view mode of the viewport. We can see we are in the lit view mode on the viewport. We can click this and we can change this between different view modes. For example, we have this unlit mode and it says renders the scene with no lights. Okay, so now we can see our scene without any lights here. So this is a good place to start working. So in Crystal Cavern, the player controls a sphere that has physics simulated on it, and we're going to navigate around the level and collect these little pickups. Now we're going to design the level with these kind of pitfall gaps between the floors as we move along. So our level blockout is going to contain some floors, and we want to make sure that we have some gaps between them. And then we can just add some simple walls around them. Okay, so we have walls, we have the floors, and we have the gaps between the floors. So your challenge right now is to try and design a simple level blockout such as this. So using the BSP tools and what you've learned from section 1, just pause the video here and try block out a simple design such as this. But don't worry if you can't remember, because in just a second I'm going to walk you through the process. So to block out this little design, I first want to make sure that I'm in the unlit view mode. I'm going to change the location of my box brush to 0, 0, 0. I can focus the box brush in the viewport by pressing F. And I want to take a look at adjusting the height of this box brush. This is going to be the floor. So I'm going to change this Z height here, or the Z brush shape, to 20. This is 20 units or 20 centimeters. And we can adjust the width of this. This is going to be the Y direction. We can adjust this to 1000. And now I want to change the length of this floor piece. To do this, I'm going to use the geometry editing mode, and we can find this on the modes panel. With this selected, I can select this face here, and with the snapping turned up, I'm just going to drag it out to give me more of a longer floor piece here. Now I want to create that little gap here. So there's two ways we could do this. We could use additive and subtractive brushes, or we can just take the floor and just hold left alt and duplicate it over. So I've got a simple little gap here. I might just give it more of a gap by dropping the snapping size and just moving it over there. Okay, I'm going to use left alt again and drag to duplicate and get an even larger gap here. Okay, so now all that's left is to get the walls in here. So to do the walls, I'm going to drag out another BSP box brush. I'm going to change its location to 0, 0, and I'm just going to leave it at 100 because now this sits perfectly on top of the grid. Now I just need to move this to the side to make it a wall, and I want to adjust its height, so I'm going to use the geometry editing mode and select the top face and just move this up, say to about this kind of height here. Yeah, that's good. And then we can find the face that's pointing in the same direction as this red arrow. I'm going to select it, and I'm just going to drag it so I can change the length of this wall. Okay, we can hit escape to deselect it, and escape again to completely deselect that. We can come back to the place mode, select the wall, and hold down left Alt and drag to duplicate it to the opposite side. So now that we have our level blocked out, let's take a look at adding some lights into our level. So to do this, we can find lights on the modes panel. We have the light section, and we have some different light types here. Let's just work with the directional light. Before we drag it out, let's change the view mode from unlit back to lit. So everything's really dark, but if we drag out the directional light now, we can see that it's a lot brighter. Okay. When we have the light selected, we can change its intensity on the details panel. So we have the intensity here. We can click and drag this slider to adjust that. But notice what happens if we bring the intensity down quite low. I'm going to set mine to 1.5. Okay, so it's made it darker, but look, it's ever so slightly kind of getting brighter and glowing. So this is a default post-process effect that's active in Unreal. It's called auto exposure, but it's also known as eye adaptation. And we can disable this by coming up to Edit, and then Project Settings, and then under Rendering, if we were to scroll down, we can find the default settings here. Okay, we can uncheck auto exposure, and now when we close this and return to the level, we can see that it's no longer glowing and changing the lighting here. So I'm going to keep mine quite low to around 1.5. Now we have this mobility section just above the intensity. The light is a stationary light. We have static. If we were to click this, we can change it to a static light. Look, it says lighting needs to be rebuilt, 16 objects. Okay, we have movable as well, and that message now goes away, and it also goes away when it's stationary. So what's the difference between all of these lighting modes? So if our directional light was set as a static light, this means that all lighting calculations are pre-built. This is also known as pre-computed lighting. Well, what does this really mean? Well, this means that there's no real-time lighting calculations being done. There's no real-time shadows. Because of this, we cannot move or change the color of the light during runtime. So if we wanted to set up a scenario where we move through a trigger box and the light color changes, we can't actually do that with static light. So there's some limitations here with them with regards to real-time gameplay. So this is why we see the message lighting needs to be rebuilt, because the lighting needs to be recalculated in the editor. It can't be figured out at runtime. So because of this, it's actually really cheap to render these lights. It's actually really good for the performance of your game to use static lights. Stationary lights are used as a trade-off between pre-computed and real-time lighting. So what does this mean? Well, stationary lights can cast real-time shadows. For example, if we had a character running around underneath a light, we would naturally want to see their shadow moving with them, and stationary lights allow this. But at the same time, if we had a static piece of the environment that would never move, such as a wall, then a stationary light would allow us to pre-compute the lighting for the actor. So we have the best of both worlds with stationary lights. If we had movable lights in our level, we would notice these little arrows around the lights showing us that they are movable. This is just a little editor icon letting us know that. Movable lights use fully dynamic lighting. There's no need to rebuild lighting at all for these. They cast dynamic real-time shadows for every single object, in turn making them a bit more expensive to render, but they are still totally usable to use in-game. Anytime you want to look at this information, all you have to do is just hover over static, stationary, or movable, and it will give you this information. Okay, but I'm going to leave my light on stationary, and I'm going to build the lighting. To do this, we can drop down this little arrow next to build on this top bar, and we can just use build lighting only. We have different lighting qualities. I'm just going to leave mine on preview, and we're just going to hit build lighting only. So the engine is now pre-computing the lighting for our level. This won't take too long for a level of this size, but the more static actors in a level, the longer it will take to build. So it's now complete for me. I want to save all my changes by coming up to File and then Save All. Okay, great. So that's the end of this lesson. You now know how to add lights to your level and also how to use pre-computed or dynamic lighting. Hey, welcome back. This lesson is point lights, spotlights, and skylights. In this lesson, we're going to be taking a look at lighting our level with different light actors. And we're also going to add materials to our level blockout. So in the previous lesson, we added in a directional light. So it's lighting our scene just very gently, but we also have these very dark shadowed areas on the walls where we don't actually have any light casting against them. Okay, we're going to take a look shortly about how we can fix this, but let's take a look at adding in different types of lights that we can use to light our level. I'm going to come over to the other side here, and I'm going to come to the light section on the modes panel, and we've taken a look at the directional light. Let's drag out a point light. So if we drag out a point light is just a simple light that gives us a radius with it and emits light within this radius. We can adjust the radius on the details panel. We can see we can make it larger and smaller. This doesn't change the brightness of the light. To change the brightness of the light, we need to adjust the intensity of it here. We can also change the light's color just by clicking this white bar here. It brings up a little color picker, so we can just click around and just drag our mouse to change the colors here. So I'm just going to give it a nice little blue tint here. Okay, so that's pretty straightforward with the point light. The spotlight is pretty straightforward as well. We can drag one of these out. So a spotlight simply just points a light in a direction, and we can see the arrow here telling us where it is. We see the light cone as well. We have the attenuation radius to change the length of the light. We can adjust the intensity, but we also have this inner cone angle and outer cone angle for this. With the outer cone angle, we can adjust this cone shape here, but this inner cone is set to 0. But if we bring this up, it adds an additional cone, and it gives us this kind of soft fall off for the light here. We can see this if we press G to hide the editor view. We can see this little soft fall off with that, and again we can change the color of these lights. Okay, we can even make the cone angle quite large so it kind of emits onto the walls. So this is how we can use the spotlights. Moving on, we have the rectangle light we can drag out, and this is just basically used almost like a wall lamp or a TV screen if it was emitting lights from a TV screen. So we don't really have any need for using this light right now in our game. So I'm going to remove this one, and we're going to move on to the skylight. Okay, we drag out the skylight. Nothing's actually happened visibly in our scene. We have different settings here. We have an intensity and light color. If we change the color, nothing's happening in our scene. If we change the intensity, nothing's happening. And if we change it between static, stationary, and movable, nothing is happening either. So what is a skylight? Well, looking at the Unreal Engine documentation, it tells us that a skylight captures the distant parts of your level and applies that to the scene as a light. So what does this mean? Well, basically, if we had a sky in our level, it would capture the light and the colors of the sky, and it would apply that as an ambient light throughout the level. Now, of course, our scene is completely dark and there's no sky at all, so this doesn't apply to us. So what else can we do to use a skylight? Well, it says here you can also manually specify a cube map to use, and we do have access to a cube map inside our project. With our skylight selected, we can change the source type on the details panel. So it's currently set to captured scene, but we don't really have much of a scene to capture to use as ambient lighting. We can drop this down and we can choose the specified cube map. And now we have access to this cube map section here. It says none, but we can click this and drop it down, and Unreal gives us a default cube map that we can use. So what does this do? Well, when we select this, we can see now that we've got a ambient light kind of just going on throughout the whole of our level. We can control the intensity of it, and look, if we set it to 0, this is what it looks like without it. Okay, so there's really dark shadows going on everywhere. But if we bring it up to, just maybe about 0.6, so this just gives us some subtle lighting in our scene. Now, of course, we can change the color of the skylight as well, just to tint it. So really, a skylight is using a captured scene to provide ambient lighting throughout our level, and we also have the ability to tint the lighting. So right now, I have a challenge for you. using the starter content materials, I want you to apply some materials onto your BSP brushes. Have a close look at the materials you're using and try to use some rocky or stone-like materials. And now that we've taken a look at the different types of light actors, I want you to light your level using these lights. So pause the video here and light your scene, and when you're ready, come back to the lesson and hit resume. So in my level, I've just used these spotlights and I've tinted them with a blue colour, and I've also used this inner cone angle and outer cone angle to kind of give us this little soft lighting look here. And I've used the cobblestone smooth material from the starter content on the floor. But the walls I purposely left empty, just to remind you that we can multi-select actors by selecting one, and then I can press Control and select another actor. And now with the geometry section on the details panel, I can choose Select and then select all adjacent surfaces, and I can drag and drop a material onto this. I'm just going to use the rock basalt material just here. We can take a closer look at our level by focusing the viewport and pressing F11 to toggle into full screen mode. This is also known as immersive mode. So that's it for this lesson. In the next lesson, we're going to start taking a look at blueprint classes. Hey, welcome back to this lesson, which is Blueprint Actor class. In this lesson, we're going to break down what makes a blueprint actor, and then we will move on to creating our own blueprint actor that we can place in our level. So we have our level with some spotlights in it and some materials applied on our BSP brushes. So we want a way where we can represent where the player is going to start, and we can just use the player start for this from the basic tab. We can just click and drag this out into the level and plot it down. We want to make sure it's at the start of our level, and how can we do that? Well, if we select the floor, we can see that its location is at 0, 0, 0. So this is the starting area of our level. We can plot the player start anywhere around here. So let's move on to blueprint classes. Let's take a look at creating our first blueprint actor. Inside my content browser, I'm just going to right click and create a new folder, and I'm just going to name this blueprints. Okay, and we can come inside this folder, and here is where we can create our blueprint. So there's different types of blueprint classes we can create, and we're going to start with an actor. We're going to begin creating a collectible crystal. In our game, as the player moves through the level, they will be able to collect these crystals, and these crystals have very specific requirements and behaviors. Let's break these down. So the crystal needs a mesh so we can visually see it in the level. It's going to need a trigger of some sort to allow the player to collect it. We might want to add some motion to it so it spins. We could also make it bob up and down. And for a nice effect, we can make it emit light. So there's a lot going on with the individual crystal. But here's the important part. We need it to have reusability. We need to be able to easily place these crystals in our level without having to program each one individually. And so this is where blueprint classes are really powerful, because we can create a blueprint actor class for this crystal that contains everything I have just listed. And blueprint actors are reusable. We can add as many of them to our level as we want without the need of having to individually code each one. Let's break down a blueprint actor. We're going to end up with this blueprint crystal, and this is the blueprint actor, but we can think of an actor as a container. An actor contains components. So what do I mean by this? Well, here we see the final crystal blueprint, and it's made out of different components. It has some static mesh components, it has a sphere trigger component, and a point light component. All of these components are contained within the actor, but we can see that it's the components that make the actor what it is. And one of the most powerful features of these blueprint classes is that they have their own blueprint graphs. So blueprint classes can also contain code. So how do we go about creating a blueprint class? First, make sure you are in the correct folder within the content browser, and then where we see drop files here or right click to create content, we are going to right click to create content, and here we can see a blueprint class. that we can create. So if we select this here, it's going to ask us what type of blueprint class we want to create. So there's many different classes to choose from, but we know that we want to create an actor class. So let's focus in on the actor for now. The actor is just here, and it says an actor is an object that can be placed or spawned in the world. So this is exactly what we need. Let's select actor, and let's just give this a name. I'm going to name mine BP underscore crystal. Okay, we can double click this actor to open it up. So inside our blueprint, this is our first look at the interface. We have this viewport in the center, and around the interface on the sides we have this components tab, we have this details tab on the right, and down in the bottom left we have this my blueprint tab. Now we're not going to be working with this my blueprint tab, so I'm just going to go ahead and close this. So we just have the components tab, we have the viewport and the details tab. So where should we start? Well, let's focus in on the viewport for now. The viewport shows us what our blueprint looks like, and it allows us to affect the transform of components that we add to our blueprint. Of course, we just created our blueprint, so it doesn't really look like much right now, but we do see this white circle in the center here. This is actually a component that gets created by default when we create a blueprint actor class. So this is the root component of the blueprint. Let's look at the components tab on the left tab here. So the components tab shows us a complete list of all the components that make up our actor, and we just have this default scene root. This is actually what the white sphere represents here. It's the default scene root, which is the root component. So what is a root component and why do we have it? Well, let's break this down. Let's say we have an actor blueprint. In our case, we have our crystal. As we've just seen, this has a root component when the actor is created. Now, an important thing to note here is that every actor that we want to place in a level or we want to exist in a level needs a root component. We know that from working with actors in the previous section that actors have a transform. We can move them around, we can rotate them, and we can scale them. But here's the important thing. The actual transform of an actor comes from its root component. So when we affect an actor's transform, such as moving an actor through the world, really we are just moving its root component. So it's the root component that gives an actor its transform. And there's another thing to be said here. In Unreal, we can add components to actors. As an example, you can add a static mesh component, you can add trigger components, and you can add light components. But when we add components to an actor, they automatically attach themselves to the root component, so they become children of the root. You can think of the root component as the parent for all the components in an actor. So when we move an actor, or when we move the root component of the actor, all the children components follow it. Now let's take a look at adding in our first component. To add in a component, we will come up to the green Add Components button on the Components tab. We'll click this, and we can see a list of all the components that we can add to an actor inside Unreal. Now we're just going to focus in on adding in the static mesh component. So let's just select this. We can see we've added it in. We can see that this little white arrow is next to the default scene root. This means that it now has a child. So the root has a child, and the child is the static mesh. Notice if we select the default scene root, we can't move it because it's the root, but we can move the static mesh because it's a child of the root. Now it's a static mesh component, but it doesn't have any mesh assigned to it. With the static mesh component selected, we can see on the details panel that it looks very similar to the details from when we work in the level. But look, we have this static mesh slot here. Remember, when we assigned materials from the content browser, we can also assign static meshes from the content browser. So to do this, we can come back to the level and the content folder, and then the starter content folder, we have the shapes, and we can assign any of these shapes here just by selecting a shape and then coming into the blueprint and hitting this little arrow on the static mesh slot. So now you know how to add static mesh components to your actor blueprint, and you know how to assign meshes to the component from the content browser. So right now I have a challenge for you. In your blueprint, I want you to create 2 static mesh components. And then I want you to assign a pyramid shape from the starter content to the static mesh slot on the components. And then try rotating one of the components to make a crystal. So pause the video here and give it a go, and then come back and hit resume and I'll walk you through the process. Okay, so let's take a look at how we can do this. So I've moved my static mesh component, so it's no longer in the center of my actor, but I want it reset back to the center. So to do this, with the component selected, you can just hit this little yellow arrow on the end of the location transform, and that simply resets it back to 0 there. Okay, and now we want to assign a static mesh to this. We can drop it down here and select the mesh, or we can come back to the level and we can come to the content folder and then the starter content, and then inside the shapes folder we can choose a shape here. So we have a shape quad pyramid or a shape tri pyramid. I'm going to use the quad pyramid. I'm going to select it, come back to my blueprint, and because it's selected in the content browser, I can use this arrow here to assign it to my static mesh component. Okay, so we've got 1/2 of this crystal working. Now let's add in another static mesh component. And because we've got that mesh selected in the content browser, Unreal is automatically going to suggest and assign that mesh to us when we add a new static mesh in. Okay, so this is pretty handy. We can just go ahead and rotate it by switching to the rotation tool, and we can rotate it 180 degrees there to give us this kind of crystal-like shape. But notice what's happened to the hierarchy here. We have the default scene root, which is the parent of the parent's component of our actor. We then have this static mesh component, and then we have this shape quad pyramid, which is also a static mesh component, which is a child of this static mesh. So it's getting a bit crazy. Let's rename these right now. I'm going to select the first static mesh and hit F2 to rename it, and I'm just going to name this crystal top half. And then the second one is going to be crystal bottom half. So the crystal bottom half is a child of the crystal top half. What does this mean if it's a child? Well, if I move the crystal top half, the child is going to stay with the parent. If I scale the parent, it's also going to scale the child there. I can also reset these back to default here to reset them back. Okay, I'm going to hit compile and save, and then come back to the level. Let's come back to where our blueprint is, and let's just drag it out into the world. Okay, so we can see it's kind of large. We might want to scale it down. We can compare the size of it by selecting the player start and seeing the capsule size. So that's pretty large. I'm going to scale this down to about, let's say about 0.4. Okay, that's looking like a good size, and we can add these as many times as we want just by dragging them out from the content browser. So we have some reusability with this blueprint that we've just created, and we can alt drag to duplicate them as well. So we're going to wrap up this lesson here now, because we can't really take this much further without our player. So in the next lesson, we're going to take a look at creating a player pawn so we can move around the world and start collecting our crystals. Hey, welcome to this lesson which is about player pawns. In this lesson, we're going to lay the foundation to our player pawn by creating its blueprint class and setting up its components. We'll learn how to adjust cameras with spring arms, and we'll also wrap up this lesson by replacing the root component. So let's begin creating a player. Naturally, you might want to say player character, but we're going to have a physics sphere as our player. It's not so much a traditional humanoid character. So character is not the correct term for us here. In Unreal, what we are trying to create is known as a player pawn. A player pawn is an extension of the blueprint actor class we used in the previous lesson. And looking at the Unreal documentation, it tells us that the pawn class is the base class of all actors that can be controlled by players or AI. And it also tells us that a pawn is the physical representation of a player or AI entity within the world. So what this is telling us is that the pawn class can be used for our player. Great, so this is what we want to use. So where do we get started with creating our player pawn? First, let's come inside our blueprints folder and let's right click here to create a new asset. We're going to create a new blueprint class. And just beneath actor, we see pawn, and it says a pawn is an actor that can be possessed and receive input from a controller. So there's two new terms here that we haven't seen before. The first is possessed and the second is controller. We will start breaking these down as we move forwards with this class, but for now I'm just going to select pawn and I'm just going to name it BP underscore player pawn. I'm just going to double click on it to open it up and I'm going to dock it next to my level. And right now I have a challenge for you. I want you to add components to your player pawn. I want you to add a static mesh component, a camera spring arm component, and for your final one, I want you to add a camera component. So try adding these, and don't worry if you're a bit unsure, because in a few moments I'm going to take you through the steps to do this. So pause the video here, and then when you're ready, come back and hit resume. Okay, so let's take a look at how we can do this. We've just got our default scene root, our roots components here. Now let's add in a new static mesh component. We'll hit add component and then select static mesh. Now we can name this something here. I'm just going to name this mesh. And I want to assign a sphere to the mesh slot. So one way I can do this is by coming over to the static mesh slot, I can drop down where it says none, and I can look through the different shapes here, or I can just type and search for sphere, because we want it to be a sphere. I'm going to choose the shape sphere here. Okay, so we've got our sphere, and now we want to have a camera that tracks the player, and we can add cameras directly in as components, but first we want to add a camera spring arm that we can attach a camera onto, and this makes it much easier for adjusting the camera for us. So to do this, we can come up to add components again, and we can scroll down a bit till we get to the camera section. We can see there's a camera here, but there's also the spring arm. So let's go ahead and just select the spring arm. We don't have to name it anything. I'm just going to deselect it. And now I can just go ahead and add the camera. So I'll come up to add component and then scroll down again and choose the camera. And now let's take a look at our component hierarchy. I don't have to name this camera anything as well, so I'm just going to deselect that. So we've got the default scene root. We can see this little arrow here expanding it. So all the components we've added are now a child of the default scene root. We can see we have the mesh that also has an arrow, and we can see that the spring arm is a child of the mesh. So if I close this down, we can see that the camera is separated. So the camera isn't actually a child of the mesh yet, but the spring arm is. When we select the spring arm, we see this red line coming out showing us the length of the spring arm. Let me just move this up so we can see this. Now we want the camera just here in the viewport we want this to be on the end of the spring arm. So how can we do this? Well, we want the camera to be a child of the spring arm. To do this, to make the camera a child of the spring arm, we can just click and drag it up onto the spring arm. We can see the camera's moved. If we select the spring arm, we can see the camera's not actually on the end of the spring arm there. So how can we reset the camera to the end of the spring arm? Well, we can select the camera, and then on the details panel where we have the transform for the camera, we can reset its location by hitting this yellow arrow button just here, which sets its relative location to 0, 0, 0. Now let's select the spring arm, and like I said before, the spring arm is going to give us greater control over the camera, specifically how we place it around our sphere. On the details panel, we have this target arm length, and when we adjust this, it's going to change the length of the spring arm, but because we have the camera attached to the spring arm, it changes the location of the camera. The same goes when we rotate the spring arm. The camera moves with the spring arm, giving us the effect that we are rotating the camera around our sphere. And looking at root components again, we know that a root component is needed. We currently have the default scene root as our root component. But what I haven't mentioned is that root components can actually be changed. So we can get rid of the default scene root and just have our mesh as the root component. To make the mesh the root component and to delete the default scene root, all we need to do is drag and drop the mesh component onto the default scene root, and here it says drop here to make mesh the new root. The default root will be deleted. So when we do this, It deletes the default scene root, and we now have our sphere mesh as the root component. Great, so I'm just going to finish up here by hitting compile and save. In the next lesson, we're going to be learning more about controllers, input, and possession. Hey, welcome to this lesson, which is controllers and possession. In this lesson, we're going to be taking a look at player controllers, and we're also going to find out what it means to possess a pawn. So in the previous lesson, when we created our player pawn, we briefly saw the terms possessed and controller. In this lesson, we're going to start breaking these terms down to understand what they mean and to understand how Unreal handles players. Specifically, what allows a player to control a pawn. So we have our player pawn blueprint in the content browser. Of course, it doesn't do much right now as we haven't done any blueprints programming for it. However, we did add in a mesh component and also the camera components for it in the previous lesson. Now, what do we want to do with the player pawn? Well, really, when we play our game, we want to play the game as our player pawn. We want to be able to press the play button on this toolbar and have the viewpoint of the player and to be able to send input to it so we can control it. So what happens if we press play now? Well, we just spawn in as the default player pawn that we saw in section 1. We're not playing as the player pawn that we created, we're playing as the default one that Unreal spawns in when we play the game. Well, I'm just going to hit escape. We have our player pawn in the content browser. What happens if we drag this out into the world and now hit play? Well, it still doesn't work. We're still controlling this default pawn. We're not controlling or having the viewpoint of our player pawn. So why is this? We have the player pawn sitting here, but we can't control it. How do we go about controlling it when we play the game? How do we be it? Well, this is where controllers and possession come into play. Every player in Unreal has a player controller. Now, I don't expect you to understand what a player controller is yet, but we're going to start exploring this together. Notice that in my level, in my world outliner, I have 18 actors. And keep an eye on this. When I hit play, I now have 30 actors in my level. With the viewport focused, you can press Shift F1 to bring the mouse back, and you can start scrolling down the world outliner to see the list of your actors. And notice that you'll have some actors that are listed in yellow here. Yellow actors in the world outliner mean that they have been spawned in by the engine at runtime. These haven't been manually placed by us in the viewport before we hit play. Okay, so we have a bunch of different actors that are spawned in when we hit play. And notice that one of them here is actually a player controller. If we scroll all the way up to the top, I also have an AI controller here. So there's two different types of controllers, an AI controller and a player controller. Now don't think of these controllers as Xbox or PlayStation controllers. Think of these instead as an invisible actor that exists in the world for each player playing your game. In the controller section of the Unreal Engine documentation, it tells us that controllers are non-physical actors that can possess a pawn to control its actions. And we know this is true because when we press play, we have controllers in our level that we can't see, so they are non-physical. The documentation also tells us that a player controller is used by human players to control pawns, while an AI controller implements the artificial intelligence for pawns they control. So we have two different controllers mentioned here, player controllers and AI controllers, both of which we've just seen in the world outliner. And on the documentation, we have subcategories for each of these controllers. Let's just take a brief look at the player controller. This tells us that a player controller is the interface between the pawn and the human player controlling it. The player controller essentially represents the human player's will. Okay, so let's try and make sense of all of this. Unreal has AI controllers and player controllers. Every player has a player controller. As we've seen in the documentation, a player controller represents the player's will. As an example, if I am a player, my player controller tells Unreal which pawn I control. It tells Unreal which pawn listens to my input. And how does it do it? Well, a player controller does this through possession. Player controllers allow players to possess and unpossess pawns, and this really means it allows players to take control or stop controlling a pawn. And a final important thing to note is that a player can only possess one pawn at a time. So what we really want to do when we play the game is we want to possess this pawn that we have in the level. So how do we do this? Well, there's different ways we can do it. I'm just going to show you one way for now. We can select the pawn, and then on the details panel we have a pawn category, and under here we have auto possess player. And this tells us when we hover over it, it says determines which player controller should automatically possess the pawn when the level starts. So this is definitely what we want to use. We can drop this down where it says disabled and we can choose a player. Now we're creating a single player game here, not a local multiplayer game, so we're just going to select player 0. And now when we hit play, we have possessed our player pawn, or really our player controller has possessed the player pawn. And we now have a different camera view. We are viewing the world through the player pawn's camera. Remember that we added in a camera component to the blueprint class, and we can now think of this as the player camera. Now our camera is a bit close to our sphere here, so right now I have a challenge for you. I want you to adjust your player camera, but be careful when I say this. I'm going to drop you a hint here. Do you want to adjust the camera component, or do you want to adjust the spring arm component? I just want you to adjust your camera view so it's a bit more zoomed out and we can see more of the world. So pause the video here and have a good go at it, then when you're ready, come back and hit resume. So to do this, I'm going to switch over to my player pawn blueprint, and I don't want to change the position of the camera itself. Instead, I'm going to select the spring arm component and I'm going to use the target arm length to adjust the location of the camera. If we make this a larger value, it's going to make the camera more zoomed out. And I'm just going to use a value of about 1,400 here, so around 14 meters. And then we can switch to rotation mode if we want to, and we can make it look a bit more down onto the sphere if we want it to look like that. So I'm just going to hit compile and save and close the blueprint, and now when I hit play we can see that we're more zoomed out and we look down onto the sphere. Now if you remember, when we looked through the world outliner when we hit play, we had an AI controller here as well, but we no longer have that. So why is that? Well, at first we weren't possessing this pawn. If we were to drag in another one and hit play, we will now have an AI controller. If we were to drag in one more, we would have 2 AI controllers. And the reason for this is because we are not possessing these 2, and by default, if it's a pawn, Unreal will spawn an AI controller if it's not going to be possessed by a player. And the difference between us controlling this pawn over these 2 is the fact that we're possessing this pawn here. Now I'm just going to hit stop. I'm going to delete these 2 extra pawns we've added, and we're going to end this lesson here. Just make sure you've saved your current level by hitting the Save Current button on the toolbar. And in the next lesson, we're going to be taking a brief look at game modes. So when you're ready, I'll see you in the next lesson. Hey, welcome to this lesson, which is about game modes. In this lesson, we're going to make it so we can spawn in at our player start. And to do this, we're going to create our own game mode blueprint class that will allow us to override spawning in as Unreal's default pawn. So in the previous lesson, we placed in our player pawn blueprint class into our level and we auto possess it when we hit play. So this way works, but notice this isn't actually using our player start actor that we've placed in our level. And look what happens if we remove the player pawn from our level and just hit play. Notice that we still spawn in as Unreal's default pawn. So what is causing this behavior? Why are we forced to play as the default pawn when we hit play? Well, this behavior is all down to a specific class known as the game mode. The game mode class controls the rules of your game. For example, if you were creating a multiplayer game, you could have your own game modes for different game types, such as a Capture the Flag game mode class or a King of the Hill game mode class. But of course, we're not creating a multiplayer game right now, so what else does a game mode do that applies directly to us? Well, the game mode determines default classes for your game. For example, it's the game mode that assigns the default pawn class, meaning it determines which pawn we spawn in and play as. The game mode also handles spawning the player pawn at the player start actor in your level. And one thing to note is that for each level, you can override the game mode via the world settings. You can have different game modes for different levels. The game mode also has its own event graph and can execute blueprint code. And there's more to the game mode that's relevant to us right now. When we press play or when we start the level, the game mode executes some behavior. So what does it do? Well, when the player enters the game mode will spawn a player controller for that player. The game mode will then find the player start in your level, and then it will spawn the default pawn class at the player start. Then the game mode makes the player controller possess the default pawn. So this is what's really happening when we hit play. This is why we get this default behavior. It's the game mode that is causing us to spawn in as Unreal's default pawn at the player start. But we can change the default pawn class by creating our own game mode blueprint. So we want to create our own blueprint game mode class. In the content browser, we know that we can right click to create a new asset. So right now, I have a challenge for you. Inside your blueprints folder, I want you to create a new blueprint class. When Unreal asks you which class you want to create, make sure to choose Game Mode Base. And I want you to name this class BP_game mode. So pause the video here and have a go at this, and then when you're ready, come back to the lesson and hit resume. So to do this, we want to make sure we're in the blueprints folder in the content browser. Inside this folder, we can right click to create a new asset. We're going to create a new blueprint class, and we're going to choose Game Mode Base. And notice it says Game Mode Base defines the game being played, its rules, scoring, and other facets of the game type. So let's choose this, and we're going to name it BP_game mode. Now let's double click on this to open it up. So the interface is the same as other blueprint actors that we've been working with, but I wanted to show you a little trick here. If we close the game mode and reopen it again, it gives us more of a compact view, showing us the game mode defaults that we can change. And look, we have a classes section here, and there is a default pawn class, and it's assigned Unreal's default pawn here. So we can simply drop this down and choose our BP player pawn. And this is all we need to do in here for now. We can hit compile and save, and we can close this out. If we hit play, we still don't spawn in as our default pawn, and this is because we haven't assigned our game mode. So there's two ways we can do this. Let me show you one way first. We're going to go up to settings on the toolbar, and this is where we can find the world settings. When we select this, it opens it up on a new tab next to the details panel, and there is a game mode section here, and look, it says game mode override, and it's set to none currently. So when it's set to none, it's going to assign Unreal's default game mode, but we can drop this down and override the game mode for this level by choosing our BP game mode we just created. And now when we hit play, we spawn in as our player pawn. But what if we don't want to override the game mode and we want to set our BP game mode as the main game mode across every level in our game? Well, to do this, we want to come up to Edit and then Project Settings. And here we have Maps and Modes. When we select Maps and Modes, it shows us default modes and it says default game mode. And it's assigned Unreal's default game mode, which is known as Game Mode Base. But we can drop this down and choose our BP game mode just here. And now we can close this. And now any new levels we create will have our BP game mode assigned to them by default. Great, so in this lesson we've learned how to override spawning in as Unreal's default pawn, and we have done this by creating our own game mode blueprints class. So that wraps up this lesson. In the next lesson we're going to continue developing our player pawn. Hey, and welcome to this lesson, which is all about applying physics to the player pawn, and also tackling the challenges that arise with the camera when we do this. We'll also be learning about how components retain their relative transforms. Okay, so we now spawn in correctly with our player pawn. Now, to make our player pawn move throughout the world, we want it to have a physical presence. So to do this, we want to apply physics to it. Now, there's going to be some issues that arise after we do this, but we're going to tackle those issues together. For right now, I'm going to start off this lesson with an early challenge. I want you to open up your player pawn blueprint, and I want you to enable simulate physics on the root mesh component. So pause here and have a go at this. Okay, so let's have a go at doing this. Let's open up our player pawn blueprint and let's select the root component, which is our static mesh components here. Now to apply physics to our sphere, we just need to come to the details panel, and where we have the physics category, we can simply check simulate physics to do this. Now remember, we have our camera components here, and we can see that the camera component is a child of the spring arm component, meaning the camera is attached to the spring arm. But the spring arm is also attached to our mesh components that we've just applied physics to, meaning that when our sphere moves and falls because of gravity, the camera is automatically going to follow it. If we come back to our level, we can take a look at this just by moving our player start up into the air, and we can hit play. So we can see that the sphere drops down and the camera moves with it. But let me show you what also happens. I'm just going to grab a cube off the basic tab on the modes panel. I'm just going to scale it up so it's kind of like a ramp here. Okay, and now let's take a look at what happens when I hit play. So the sphere falls, but it looks like the camera immediately starts freaking out when the ball starts rolling. So why is it doing this? Well, this is because the spring arm is retaining its relative rotation. So what do I mean by this? Well, by default, components will retain their relative transforms to the parent they are attached to. So for example, we have our mesh component with the spring arm and the camera. Now the spring arm is a child of the sphere. If the spring arm component is rotated by 60 degrees on its pitch, this would mean it's rotated 60 degrees relative to its parent. And even if the rotation of its parent changes, the spring arm will always be rotated by 60 degrees when compared to its parent. This is what I mean by retaining its relative rotation. The spring arm component is retaining its relative rotation to its parent. In effect, when the sphere rolls, the spring arm rolls with it, and this is what our issue is. We don't really want our spring arm to roll and rotate with the sphere. So is there a simple solution to this? Well, yes, there is. Instead of the spring arm retaining its relative rotation, we simply want it to retain its world rotation. So let's take a look at doing this. I'm going to switch back to my player pawn, and with the spring arm selected, we can see the transform section on the details panel. Now the values listed here are relative to the spring arm's parent, which is the mesh component. Now our issue is with the rotation method of the spring arm. We can change the rotation method or override it by clicking on this rotation here, and we can change the rotation type. It's currently set to relative, and this says rotation is relative to its parent. We can change this to world. And now when we come back to the level and hit play, we can see that the spring arm no longer rotates with its parent. Okay, but we might notice a bit of camera bobbing here with the spring arm. So the reason we're getting a bit of camera bobbing is because of the placement of the spring arm component. We want to make sure its relative location is in the center of the sphere. So to do this, I'm just going to change the location, or the Z location, from 67 to 50 on the spring arm, which centers it there. And now when we come back to the level and hit play, we no longer have any of these issues. Okay, great. So that wraps up this lesson. I'm just going to remove this ramp here and bring my player start back down to the floor. And I'm also going to hit File and Save All to save all my assets. So we're pretty much ready to start adding movement input into our player pawn. And that's just what we're going to start doing in the next lesson. So when you're ready, I'll see you there. Hey, welcome to this lesson where we will be covering event graphs for blueprint classes, and we will also be looking at setting up custom input mappings for player input. So we want to start adding some input to control our player pawn. In the previous section, we were just utilizing the level blueprint for our blueprint programming. However, blueprint classes have their own event graphs that we can code directly into. We can find the event graph for our player pawn by switching from the viewport tab to the event graph tab. So this is the event graph. It looks the exact same as the level blueprint really. However, anything we code here is contained directly in this blueprint class. And again, blueprint classes are reusable, so it makes the coding side of things really powerful. If we coded a single blueprint class and placed 20 of them in our level, all 20 of those blueprints would execute the same code. You don't have that flexibility in the level blueprint. And the issue with the level blueprint is that any code you make is stuck in that level. So really, you would only want to use the level blueprint for very specific level events. There's some things that function in a slightly different way when we compare a blueprint class to the level blueprint. We know that we can select actors in our level, and then in the level blueprint we can right click and create a reference directly to the actor selected. But look what happens when we do this with a blueprint class. Even though the actor is selected, there is no option to create a reference to the selected actor. This is simply because you can reuse class blueprints in different levels. If we reference an actor in one level, that actor might not exist in another level. This doesn't mean that blueprint classes can't have any references to actors. You can absolutely do that, but what I'm saying is you just can't use the same simple method to reference them as you do in a level blueprint. So what's the first thing we want to do in the events graph of our player pawn? Well, we want to start by making the class respond to player input, so the player can control and move the pawn around the level. In section 1, we saw that we can right-click in the event graph and we can go to the input category. And under the input category, we can find input events for things such as the keyboard and the mouse. And we learnt that there's two different input events. There's action events, which is for simple pressed and released input, and there's axis events, which continuously fire and send an input value. However, we can create our own input mappings that can be bound to multiple inputs, and we can even give them a name. For example, we can have a single input event for moving the pawn forwards and backwards, and we can name it appropriately. So how do we access and create our own input mappings? Well, we do this in the project settings. We can come up to Edit, and then Project Settings. And there's different categories on the left. Under the Engine section, we can find Input. And here at the top we can find bindings, which is where we create our input mappings. So let's just take a moment to think about what we want to create. I want the player to continuously move forwards or backwards depending on if we press W or S, and we want them to continuously move right or left depending on if we press D or A. So we know that if we want an event to continuously fire, we want to use an axis mapping. So let's add a new axis mapping in. And let's expand the axis mappings by clicking this arrow. This is the new event we've just added in, and we can rename this. We're going to bind two inputs to the same event, so let's name it something like move forwards / backwards. And we can expand the event to choose the first binding to the input. Let's start with moving forward, so I'm just going to drop this down and type in W to search for the W key, and we can just grab that there. Now we have input scale here. When I hold W down, I want the input scale to be 1, representing moving forwards. And we can add another input bound to the same event by hitting the plus icon next to the event name. So I want this one to be the S key, but when I press S, I want it to be -1 for the input scale. This way, the direction of our movement will reverse, making us move backwards. But I'm going to let you have a go at setting this and the rest of the inputs up. So your challenge right now is to set up your input bindings for move forwards and backwards. I recommend to use the W and S keys for this, and then for move right and left, and I recommend to use the D and A keys for this. And make sure to set the input scale for each binding. So pause here and have a go at it, then in a moment I'll take you through the process. Okay, so to do this, I first want to make sure my input scale is set correctly for my S key. I'm going to change this to -1. And now we want to set up the new axis mapping for move right and left. So I'm going to add in a new axis mapping by hitting this plus icon here. And we can add in a name for this, move right / left. The first mapping is going to be my D key. And the scale is going to be we're going to leave the scale at 1, and we're going to add in another input binding, and this is going to be for the A key. and the scale here is going to be -1. Okay, we don't need to compile or anything here, we can just close the project settings to return to our player pawn. And we can find our newly created input axis events by right-clicking in the event graph, and we can come to the input category, and we can come to axis events, and here they are. We can grab move forwards and backwards, and then we can right-click again and come to input, and then axis events, and grab move right/left. Okay, so we have our input events ready to set up our movement functions. And that's exactly what we're going to be doing in the next lesson. So when you're ready, I'll see you there. Hello, in this lesson we are going to be applying forces to our mesh component to cause it to rotate. We're going to be working with torque. In this lesson we're going to be learning all about it and breaking it down. So when a player sends input to our player pawn, we want it to react and move based on the player's intended direction of movement. But remember, we aren't just moving it, we have physics applied to our mesh component. So instead of our mesh just magically floating, we want it to roll towards the direction that the player intends to move. So to do this, we want to apply a rotational force to the mesh. Torque is a force that can cause an object to rotate about an axis. You can refer to it as adding a torque to an object, or just simply adding torque to an object. In our case, we're going to be adding torque, or adding a torque to our mesh. But to simplify it, when you hear torque, you can think of a rotational force that will cause our mesh to rotate. We're going to be breaking it down throughout this lesson. Now let's just start out with the idea of rolling the mesh forwards and backwards with our input axis event that we created in the previous lesson. How do we go about applying torque to our mesh component in this event graph? To get started, we need a reference on our event graph to the actual mesh component. This is really easy to do. On the components list, we can find the mesh component, and we can just simply click and drag and release it onto the graph to create a reference to it. And with the reference, the blue output pin here, we can drag it out and release it to call a blueprint action. Now torque is a physical force, so we're going to scroll down to the physics category here, and when we expand this, we find functions relating to physics and forces, and about 10 functions down we find the torque functions. There's two different methods here. There's adding torque in degrees or adding torque in radians. While developing our prototype, adding torque in degrees gave Ben and I some unexpected results. So for now, let's just select add torque in radians. Looking at the function, we can see there's many different inputs on it. We have the target, and the target is telling us what component the torque is going to be applied to. And of course, right now this is our mesh component. Below this, we have an input named torque, and this is a vector. We know it's a vector because we can see it's giving us an x, y, and z value to work with. But not only that, in blueprints, vectors are color-coded yellow. Let's just put all of our focus into this vector input right now. When we hover over torque, it says torque to apply, direction is axis of rotation, and magnitude is strength of torque. Wow, okay, so if you don't understand how torque works, this statement might seem quite confusing or overwhelming, but don't worry, we're going to start breaking this down together right now. In Unreal, when you add torque to a mesh, it will begin to receive an angular acceleration. Imagine for a moment that our mesh is a wheel. We can visualize our x, y, and z directions. We know that x is forward in Unreal, so if we want to roll this wheel forwards, what would the torque direction be? You might naturally choose x as the direction. Because x is forward in Unreal, you might think that if we add a torque in the direction of x, our wheel will also roll forwards. Well, this isn't what would happen. Remember, in Unreal, the function told us that direction is axis of rotation. So what would happen? Well, let's visualize our rotation axes. We can see that the x-axis of rotation for our mesh is here, If the torque direction is x, this would result in an angular acceleration being applied along the x-axis of rotation. The mesh would begin to roll on the x-axis of rotation. Okay? Let's look at another example. Let's say we add a torque in the z direction of our mesh. Our z-axis of rotation is here. So what would happen here? Well, an angular acceleration will be applied along the z-axis of rotation. The mesh will begin to spin. Okay, so if we want the mesh to roll forwards, we would add a torque to the mesh along the y direction. And we select the y direction because we would then cause an angular acceleration along the y-axis of rotation, causing the mesh to roll and move forwards. So just remember, when we add a torque to a mesh, the direction doesn't mean we want it to move in that direction. The direction is the axis of rotation along which an angular acceleration will be applied. So if we want to roll and move the mesh forwards, we know that we can add a torque to the mesh in the y direction. We would make use of the y value on this vector to do this. Now, remember, I said this vector does two things. We can hover over torque, and it says direction is axis of rotation. This is the first thing that we've just covered. And the second thing is magnitude is strength of torque. Right, so this is saying that the values that we put into this vector also affect how strong the strength of the torque is. The larger the value we put in here, the stronger the force applied to our mesh will be. But remember, we want to add torque based on the player's input. We want to make use of our move forwards and backwards input axis event. If we press W, we want it to roll forwards. If we press S, we want it to roll backwards. So let's hook up the execution pin into the add torque function. Now, this isn't yet going to respond to the player's input because we haven't made use of the axis value on the event. We want this to affect the Y value of the torque. Now, the torque is still a vector, but we can split this apart to gain access to the X, Y, and Z values just by right-clicking on the pin and hitting Split Struct Pin. And we can plug the axis value from the event directly into the torque Y input. Now let's just come back to the level and hit play, and let's see what happens. We can press W and we can press S, but look, it doesn't look like anything's happening. And this is because the torque units we're dealing with have to be pretty large to take effect on our mesh. Let's stop playing and come back to the blueprint. The axis value on our event changes depending on our input. If we hold W down, the axis value is going to be 1. If we hold S, the axis value is going to be -1. Okay, so the value flips if we hold S, meaning the torque direction will be flipped, and as a result, our mesh will roll backwards. But as we've just seen, our mesh doesn't even move, and we need these values to be larger in order for the force to take effect on our mesh. The units we are dealing with are incredibly small. The units are in Newton centimeters, and the mass of our sphere is going to affect the units we need to use. But we're not going to worry too much on the exact units we need to use or on the mass of our sphere. Right now, we're just going to tweak the value to get the result we want. So how do we tweak it to get a larger result? Well, we can multiply the axis value before we plug it in to the Y input. And this is where you come in. So your challenge right now is to multiply the axis value of your move forwards or backwards event and try tweaking the value to see if you can get your mesh to roll forwards and backwards. And once you've done that, why not make use of your move right and left axis event and try and make your mesh roll right and left by adding torque. You'll have to find the torque direction to use to do this. And to help you, you can drag in a simple shape at any time and make use of the transform tools to help you figure it out. Or you can just rewatch an earlier part of this lesson to help you decide. So this might be a tough challenge. Pause here and give it a good go, and in a few moments I'll walk you through the process. Okay, so we want to multiply our axis value. We can drag it out and we can put in the star sign or asterisk, and we can grab the float multiply float and then plug this output directly into the Y input on the add torque in radians function. Now, the larger the value we put in here, the stronger the force is going to be. And if you had a go at the challenge, you'll notice you need to put an incredibly large number in here to see an effect. I'm going to put in 1 million. Now if I come back to the level and hit play, if I hold down W, I'm rolling forwards. If I hold down S, I start rolling in the opposite direction. Great. So let's have a look at rolling right or left. Now we first need to determine the torque direction. We can do this by dragging out a cube, and when we have this cube selected, we can see our translate tool. We can imagine these are the torque directions. For moving forwards, we used Y as our torque direction, and if we switch to our rotation tool by pressing E, we can find the Y axis of rotation. If we rotate it on the Y, we can see what's going to happen when the angular acceleration gets applied. If this was our sphere rolling on the ground, it would roll forwards and backwards. So we can repeat this process to figure out the torque direction for moving right and left. If we chose X as the torque direction, we should be looking at the X axis of rotation. Imagine that angular acceleration being applied here on our sphere. It would be rolling right and left. So we'll choose X as our torque direction. So let's come back to our player pawn, and let's grab another mesh components reference. We can drag this out. We can come down to physics and grab the add torque in radians function. Now we want to use the X value on the vector. We can right click the yellow pin and split it to gain access to X, Y, and Z. And we want to plug the axis value into this, but first, remember, we want to multiply this. We can grab the float, multiply float, and we can plug the output of this into the X input on the torque function, and we can use the same number we've used above to increase the amount of force that is generated when we add the torque. And we just need to hook up the execution pins. Now if we come back to the level and hit play, we can go forwards, we can go backwards, but notice here, if we try to move right by holding D, we start going left. If we hold A, we start going right. Okay, so what do we need to do to fix this? Well, we need to invert the value that we are using as a multiplier for the strength of torque. There's 3 different ways we could do this. We could simply change the input value to negative 1 million, or we could multiply this again by negative 1, which would invert it. But there's one more way I want to show you by changing the scale values of our input bindings. We can come to our project settings, and we can head into the input section. And where we have our move right and left input bindings, we can change the scale values here. D is 1, so we can change this to negative 1, and A is negative 1, so we would just make this 1. And by doing this, we are inverting the axis values. So now when we come back to our level and hit play, we can roll the player pawn forwards by pressing W, we can roll backwards with S, we can roll right with D, and we can roll left with A. So we have achieved this by making use of the add torque in radians function. We are multiplying our input axis values by a number to give us a larger force. Now this number is known as a magic number. We haven't made it totally clear what it does in our blueprint code. So in the next lesson, we're going to be making this clearer by having our first introduction to blueprint variables. Hello, in this lesson we are going to be taking a look at magic numbers and how we can counter them by using blueprint variables. So in the previous lesson we added the ability to roll the player pawn around the level based on the player's input, and we do this by adding torque to our mesh component. Now we've had to use an incredibly large number to get the result we want in our multiplier here. And this is because the torque is taking the mass of our mesh into account, and the units are in Newton centimeters. But we're not really fussed about the mass of our sphere, and we're just tweaking this number here to get the result we want. Now notice there's 2 other inputs on the torque function we haven't looked at yet. There's bone name just here, and we can ignore this because this only applies to skeletal mesh components, and we're using a static mesh component. At the bottom, we have a Boolean input for acceleration change. When we hover over this, it says, if true, torque is taken as a change in angular acceleration instead of a physical torque. In brackets, it says, i.e. mass will have no effect. So this is saying that if we set this to true, it's going to completely ignore the mass of our sphere. and we will no longer need to use such a large multiplier value, as it will immediately start applying the angular acceleration without the mass taken into account. So let's try this. Let's check the acceleration change. Let's set it to true. And this multiplier value here, let's change this to something like 12. Let's do the same below. We can check acceleration change for our move right and move left axis event, and we can change the multiplier value to 12. And now if we come into the level and hit play, notice how we still have complete control over our pawn, but without having to use such a large value for the force. Now let's come back to our blueprint. Okay, so at the end of the last lesson, I said that this number that we're using for our multiplier is known as a magic number. In programming, a magic number is a number that appears in our code without any meaning or explanation. When we view our code in blueprints, it's not immediately clear to us what this number 12 does. Okay, and magic numbers used in multiple locations can lead to issues in our code. And we have used a magic number multiple times in our code. Imagine that we want to make a change to this number and we only change it in one location, forgetting about the other location where it's used. It's an easy mistake to make that we would want to avoid. Magic numbers make it harder to change our code. So we want to avoid magic numbers, and we want to avoid them because the intention of a magic number is not clear. And magic numbers make it harder to make changes in our code. Okay, so what can we do instead? Well, we can make use of blueprint variables. Blueprint variables can be assigned a value or a reference. And the variables can be clearly named, improving the readability of our code. And best of all, blueprint variables can be reused multiple times in different locations. If we change the value of the variable, it will change it everywhere we have used it. So we only have to change the value in one place. So how do we go about creating a blueprint variable? Well, first we need to restore the My Blueprint tab to the editor's interface, and we can do this by selecting Window, and then we can select My Blueprint. Now with the tab restored, we can find a section for variables, and on the variable section on the end we can hit this button to create a new variable. And when we do this, it adds a variable in and it asks us to name it. I'm just going to name mine My Variable. Now there's different types of variables, and we can change the type that we're using by selecting the color next to it. This is indicating the type of variable it is. It says the current type is a Boolean. If we select here, we can change it and switch it to a different variable type. And we can hover over these. We can see the name of them already, but if we hover over these, it says exactly what they are. And you can even hold Control and Alt to give you some more details about the type of data. Now everything, as we can see, is color coded in blueprints. We've been working with floats here. We know it's a float because it's green, and if we hover over the pin, it tells us that it's a float. So if I change my variable to a float, I can do it here, or I can do it on the details panel with the variable selected. I can drop down Boolean and change it to float. Now looking to the bottom of the details panel, we can assign a value to it. It says default value, but it says please compile the blueprint. So we just need to hit compile, and now we can assign a value to it. We can click and drag it and use it like a slider, or we can simply type in the value. Okay, we can put in any number there, and to actually get a reference to the variable, or to get the variable and use the value in our blueprint, we can drag it out and release it, and we can hit get, and then this gets the variable. And look, it's very similar to how we've been using the blueprint references here. It adds a node in and it has a pin, and we can click and drag it to do something with it. We can release it and call a blueprint action, or we can click and drag it and plug it into something. So now it's your turn. In this challenge, I want you to create a variable. This variable is going to replace our magic number. So I want you to give the variable an appropriate name. What does the magic number do? So name it something like acceleration multiplier or torque strength, but I'll leave it up to you to come up with the name. And make sure to change the variable to the correct type. And then get the variable and plug it in to where your magic numbers are. And then the final step, make sure to assign a value to it. So pause the video here, then when you've completed the challenge, come back and resume the lesson. Okay, so I hope you've had a good go at the challenge. I'm going to remove my variable that I've created and delete it from the variables tab just by selecting it and hitting delete. Right, so I had the value of 12 in here. I'm going to type that back in. So I want to create a variable to replace this magic number that we are using on both of our multipliers here. So I'm going to hit new variable, and then I'm just going to name it acceleration multiplier. And then hit enter to confirm it. And I'm going to hit compile straight away so I can give it a value. I'm going to give it the value of 12. Now we can use this to replace our magic number. We can click and drag it out and get it and plug it straight in. And we can do this again. We can click and drag it out and get it and plug it straight in. Okay, so that's how we can create variables. But I'm going to delete it again. And I'm going to show you one more way that we can do this. If I put the value of 12 in here, we can actually right click on this input pin and we can select promote to variable. And when we do this, it automatically creates the variable for us as a float. I can just name it again. I'm just going to name it acceleration multiplier. And if you do this, just make sure that we have the variable plugged into where we multiply our move right and left axis value. And just confirm that you are using it for moving forwards and backwards as well. Now, because we promoted it to a variable from the magic number, it's already assigned the default value for us that we were using. Okay, great. So now you know how to create variables in Blueprints. We can hit compile and save and then come back to our level and play our game. We can see that we can move around just like before. But now if you want to change the angular acceleration, you can just change the default value of your variable. Okay, so that's it for this lesson. In the next lesson, we are going to be taking a look at the BSP Extrude Tool. Hello and welcome to this lesson, which is all about using the BSP Extrude Tool. So we can move around with the player pawn, but we can only move so far because we have these gaps in our floors. So what we're going to do in this lesson is create some bridges that the player has to navigate across in order to proceed throughout the level. And we're going to continue making use of the BSP brushes to make this happen. So to get started, I first want to make a slightly larger gap between my floors here. To do this, I'm going to go into the geometry editing mode and select this side face of my floor here, and we can just drag it to make a larger gap. Now I'm ready to start laying down this bridge of sorts. I'm going to come back into the modes panel, and in the modes panel we can come into the geometry section and we can drag out a new box brush. I want it to be around the same thickness as the floor. We can select the floor and scroll down on the details panel and we can see that it is 20 on the Z there. So I'm going to use that same value of 20, and on the Y here I'm going to change this to 100. Okay, and I'm just going to place this inside the floor here, and we can choose anywhere along here as the starting point of our bridge. So we know we can come into the geometry editing mode, and in the edit mode that's automatically highlighted, we can select faces and drag them to change the length of the brush we're dealing with. But we haven't taken a look at this extrude mode. When in extrude mode, you can create new geometry from existing geometry. How do we do this? Well, we do this by dragging a face. By dragging a face in extrude mode, you create new faces. Extruding allows us to create more complex shapes out of our BSP brushes. So let's look at extruding this face just here. First, we want to make sure we have the face selected, and then on the geometry editing tab, we can select extrude. Now, when we do this, it tells us that extrude only works with the local coordinate system. We're currently in the world coordinate system mode. This is what this icon means here. As soon as we hit close, we can see that it changes it to local for us, and we can toggle between that just by clicking there, but we need it on local when we are using the extrude mode. So with extrude selected, when we drag this face, we are creating new faces. Let's take a look. If I click and drag it now, we can see we've created some new faces here. These are all new faces, and we can select any one of these faces and we can also extrude these. We can switch back to edit mode, and with the face still selected, we can actually change the height of it, so we can start to see how using the edit and extrude together, that we can start to create some more unique designs across this gap here. So right now I have a challenge for you. Using BSP brushes, create pathways across gaps in your level that the player has to navigate. Make good use of the extrude and edit tools to do this. And remember, you can adjust the height of faces in edit mode. And play your level to make sure the player pawn can navigate your pathways. This might take some time to get right, it's down to you to design it. So don't be afraid to start over with it, try to come up with some interesting pathways that work. So pause here, and once you're ready, come back to the lesson and hit resume. So using the geometry editing tools with the edit and extrude, I have created my pathways. My first pathway has a little spot for a crystal pickup on it, and my second one I've opted for a under and over design here. Now all I need to do is apply some materials to them. We can select the brush and we can drop down select on the geometry section on the details panel, and we can select all adjacent surfaces and we can drag and drop a material onto it. And I'm just going to repeat this to apply the material to my first pathway. And while designing these pathways, I made sure to keep hitting play and playing the game myself to make sure that the player pawn can actually navigate across the pathways. But also while playing, I came across an issue with the camera on my second pathway. Let's take a look at what happens. You can choose where to play in your level easily by right-clicking and selecting play from here. So this is incredibly handy when designing levels. So when I play from here, when I move across my pathway and when I go under, notice the camera kind of looks like it's freaking out when I go under it. And this is happening because the spring arm component of our player pawn is colliding. By default, the spring arm component detects collisions and it auto adjusts the length of the spring arm to where the collision occurs. So we want to disable this behavior. So I want you to open up your player pawn blueprint and select your spring arm component, then disable do collision test. Okay, so to fix this, we need to come inside the player pawn blueprint. We can select the spring arm component from the components list, and then on the details panel, we can simply uncheck do collision test. Okay, we can hit compile and save, and we can close the blueprint. And now if I was to right click and hit play from here and navigate through my pathway, we can see that the spring arm no longer auto adjusts for us. Okay, great, so we have these pathway bridges that we can use to navigate across the map, but of course we can actually fall off them. So in the next lesson, we're going to handle restarting the level when the player falls off. Hello and welcome to this lesson where we create a custom box trigger blueprint that handles restarting the level when the player enters it. Okay, so we have the situation where the player can roll off the level and fall endlessly into the abyss below. Okay, so we need to come up with a solution to this. We want something to happen when the player falls off. So let's think about this. How can we detect if a player has entered or gone through a certain area of your level? You might be thinking box trigger, and you would be right. We can use a box trigger. We can find this on the basic tab here. We can drag this out. But we want to think about this situation on a higher level now. If we end up creating multiple levels for our game, we want to minimize the amount of repetitive code we have to write. If we end up using Unreal's default box trigger, we will have to do a lot of repetitive coding in the level blueprint, meaning for each level we would have to add a box trigger actor, select the actor, reference it in the level blueprint, and then add the code. It's just not going to be very reusable for us. So what can we do instead? Well, we can create our own blueprint actor that we can place in our levels and reuse. Remember that blueprints give us great reusability, as we can place them in our levels as many times as we want, and if we affect the code for a single blueprint, it will affect it for every instance that's placed across all of our levels. We're going to create a new blueprint actor, and when the player passes through this actor, it's going to cause the level to fade out and restart. So your challenge right now is to create a new blueprint actor and name the actor appropriately. Think about its function. It's a trigger, it's restarting the level when the player enters it, and we're using it as a boundary. So I'll leave the name up to you, and for the final step, I want you to add a box collision component to it. So I encourage you to pause the video here to give this challenge a go before I take you through the process in just a few moments. So we want to create a new blueprint actor. To do this, we can just right click in the blueprints folder within the content browser, and we can create a new basic asset. We can create a blueprint class. When we select this, we can choose the class. We know it's an actor we want to create, so we will select actor, and now we can just give it a name. My actor is going to be named BP underscore level restart trigger. Okay, and we can hit enter, and we can double click on this blueprint to open it. Now I asked you to add a component to it. I asked you to add the box collision component. So we can come up to add component, and we can type and search for it because there's so many components, but we can also scroll down and try find it. It's under the collision section here. We have different types of collisions here that are basically just different shapes that we can use for triggers, and we can grab the box collision component here, and if we want to name it, we can just name it trigger. Now here comes the question of the root components here. We have the default scene root and we have the trigger. We know we can click and drag the trigger onto the default scene root to get rid of it and use the trigger as the root component. But I'm not going to do this, and I'm going to show you why. It's a very simple reason. If we come back to the level and drag out the trigger, we can see we have this little white circle here showing the default scene root, and as I scale this, okay, it's going to become larger and it's going to become harder to actually select the sides of it. So I'm really simply just using this as a little handle that I can easily select in the editor there. It doesn't have any other purpose. So let's come back to the trigger and let's start doing some visual coding. We want something to happen when the player enters this trigger, or better yet, we want something to happen when an actor overlaps this box collision component. If we select the trigger component and scroll down on the details panel, we can find a section for events. If we click any of these, it's going to create the event for us directly in the event graph. So let's look at these events and think about this. We want an event for when something overlaps with the trigger. Is there anything here that relates to that? Well, yes, there is. We can use onComponent begin overlap. So let's create this event here by hitting this green plus button. Now it doesn't look like it's done anything, but if we come over to the event graph, we can see that it's created the event for us. We can see that this event has quite a few different return values on it. Now we want to check to see if the player pawn has entered this trigger. The other actor pin just here, this returns the actor that's overlapped the trigger. So we can use this pin to check and see if it's the player pawn. Let's drag it out and release it. Now how can we compare this to see if it's the player pawn? Well, we can check and see if it's equal to it. In the search bar, if we just put in the equal symbol, we have a choice of a equal or not equal function here. Okay, we can just grab the equal function. Now on this node, we have two object reference inputs, okay? It's already connected our other actor into the top pin, and we have the ability to plug in another actor to compare it. And we want to compare it to the player pawn. So how do we get the player pawn in blueprints? Well, it's really easy. We can just right click in the graph and we can type in the search bar get player pawn, and we can just grab this function which simply returns the player pawn with this return value just here. Now we don't need to worry about this player index because we're not creating a local multiplayer game, so we can completely ignore this. This has no meaning to us right now. We can grab the return value and plug it in to the second input here. And now our equal check returns this red pin, which is a boolean. It's going to tell us, or it's going to give us a true or false value. So how can we check if it's true or false? Well, we can use a branch. We could right click and search for it, or we can just hold down B on the keyboard and we can left click and it creates a branch for us. So the branch has a condition. We can hook up the Boolean pin straight into this. Let's make sure that we connect our execution pins up together. And now the branch returns true or false for us, depending on if the player pawn has entered this trigger. So how can we check to see if this works? How can we check it without using a print string? Well, we can create a breakpoint. A breakpoint will throw us directly to this line of code in our blueprint as soon as it's executed. To set a breakpoint, we can right click our branch and we can come down to where it says breakpoints here and we can toggle the breakpoint. It says the F9 is the hotkey for us here. So we can toggle this. It comes up with this yellow symbol for us. And this just means that we need to compile our blueprint. So if we hit compile, we can see it's now gone red and it's telling us now that a breakpoint is set on this branch. So what does this mean to us? Well, if we come back to our level, let's drag out this restart level trigger blueprint and let's put it underneath our level and we can simply scale it to make it larger and fit our area of the level. Now if we come into the level and hit play and just roll off the edge, let's see what happens when we fall down now. Okay, look, it's kicked us straight into our blueprint, letting us know that this has been executed. So we know that this works. We can hit stop to jump out of the game. We can take off the breakpoint by hitting F9, and now we can go about restarting the level. Now I want you to do this next part. I want you to call the function named getCurrentLevelName. This is going to return the name of the level that you are currently in. And then I want you to call the function named OpenLevel. We've already used this function in the previous section. And then attempt to connect both of these functions together in your execution flow and take a look at what happens. So pause here and give this a go, and then in a few moments we can take a look at this together. Okay, so I'm going to assume you've had a go at this now. Let's take a look at what happens. We know we want to restart the level if the player pawn has entered the trigger box. So we're going to work from the true output of the branch. I asked you to call a function named getCurrentLevelName. So let's do this now. Let's drag out the true of the branch and type in getCurrentLevelName. Okay, we can grab this function and we can see that this function returns a pink output pin here, and when we hover over this we can see that it's a string, and a string is a sequence of characters, and in the case of our function here it's just returning the name of our level as a string. Now we can drag out this output pin from the function and we can take a look at the next function I asked you to call, which was a function named OpenLevel. We used this in the previous section. As soon as this gets called, it's going to open the level with the name that's provided in here. But look, the type of data we're dealing with is a different pin color to the string here. So what is this? When we hover over this, we can see that it is a name. So what do we need to know about this? Well, the main difference that you need to be aware of here is the fact that a name is case insensitive, meaning names treat uppercase and lowercase characters as the same value. Okay, so it's not a huge biggie, but it's something to be aware of. Now we can connect these two pins together just by dragging from one of them and connecting it into the other, and we can see that it's going to convert the string to a name. Okay, so that's all we're going to do here. Let's come back to our level. We know we have our level restart trigger volume underneath our BSP geometry. We can select it, and I'm just going to make sure that this covers my whole map just by scaling it and moving it and scaling it around here. Let's take a look at what happens when we hit play. So when we hit play and we roll off the map, the level gets restarted instantly. Okay, so it works, but it's not perfect yet. We're going to spend some time polishing this up in the next lesson. And as always, I encourage you to use the lesson resources to find a link to the discussions where you can ask questions about this lesson and share your progress in the Game Dev TV community. So when you're ready, I'll see you in the next lesson. Hello and welcome to this lesson, which is all about fading cameras in and out by using the Player Camera Manager. Okay, so we want to take a look at polishing up the process of restarting the level when the player falls off below. To help make this happen, we're going to be making use of the Player Camera Manager. The Player Camera Manager is spawned in on play, so it exists only when the game starts. We can find it in the world outliner while we are playing the game, and it is listed in yellow because it's been dynamically spawned in at runtime. It is non-physical, just like the player controller. Okay, but what actually is it? This isn't really clear. Well, you can think of the Player Camera Manager as a class that contains functions and properties that relate to the current camera for the player. Okay, but how do we use it if it's only spawned in when the game starts? Well, it's accessible via blueprints. We can gain access to the Player Camera Manager anywhere in blueprints by calling the Get Player Camera Manager function. So what does it do for us? How does this relate to our situation? Well, we can use the Player Camera Manager to call functions dealing with camera fading. When the player falls off the level, we want the camera to smoothly fade out, and then once it's faded out, the level will restart. I've given you a couple of pieces of the puzzle already, so I want you to have a go at this challenge. Inside your level restart trigger actor, get the Player Camera Manager, and then call the Start Camera Fade function. Now you're going to have to figure out where this is going to be placed and executed in your code. So have a good think about this and try inserting it into your execution flow. Then in a few moments we'll go through this together. Okay, so I hope you had a good go at the challenge. So we want to start by getting the Player Camera Manager. To do this, we can right click and simply type and search in the search bar here for the Get Player Camera Manager function. And we can just grab this here, and this blue output pin here returns the Player Camera Manager. So if we were to drag this out, we can now call actions that relate to it. And we wanted to call the Start Camera Fade function. If you had a little look around, you would see there's a camera fades category here. If we double click here, we can see a few camera fade functions, and we're going to grab the Start Camera Fade. So now we have to decide where we want to insert this into our code here. Well, let's think about this. Do we want to insert it before we do a check to see if it's the player pawn that enters the trigger? Well, no, not really, because technically any actor could enter this trigger and cause the camera to fade out if it's placed here. So we only want to fade it out once we know the player pawn has entered the trigger. So we're definitely going to be looking after the true output of the branch. But now the question is, do we want to insert it before we get the current level name and then reopen the level? Well, yes, we do, because as soon as the open level function is executed, it's immediately going to reopen the level. So we want to insert it before here so we have a chance to fade the camera out. So how do we go about inserting it? Well, we need to break the execution pins here. We can do this just by right-clicking on the true output of the branch, and we can hit break link to get current level name, or we can use the hotkeys. We can hold down left alt and left click on the true output pin, and we can move these functions along. And we can bring up our camera fade function, connect the true output of the branch into this, and then we can connect the output pin of the Start Camera Fade to the Get Current Level Name. So how do we use this camera fade function? We have these pins here named from alpha and to alpha, and we can find out what these do just by hovering over them. If we hover over from alpha, it says alpha at which to begin the fade. Its range is between 0 and 1, and where 0 is fully transparent and 1 is fully opaque solid color. Okay, so this is telling us that the value of 0 is going to be fully transparent, allowing us to see the game world, and the value of 1 is going to be fully opaque, meaning the world will be fully faded out. So how do we want the fade to start? Well, we want it to start fully transparent, then we want it to fade to a fully opaque solid color over time. So the start alpha, or the from alpha, is going to be 0, as we want to start by seeing the game world, and then the to alpha is going to be 1, because we want it to fade out. And now we have the option of choosing the duration. This is in seconds, how long it should take to fade out. I'm just going to use the value of 2 here for 2 seconds. We can change the color here if we want to. It's currently fading out to black. I'm going to leave mine fading out to black. And we can choose if we want to fade the audio. We don't currently have any audio in the game, so we can leave this unchecked. And then finally we have this hold when finished. If this is unchecked, it means that after the fade is finished, it will then disappear. So let's turn this on actually to hold the fade. Now, this is looking good. Let's come back into our level and hit play. Let's see what happens when we roll off now. So it doesn't look like anything has happened. It hasn't faded out, it's just immediately restarted the level. So why would this be? Let's come back to the blueprint and take a look. This is because the start camera fade is executing and then it is immediately executing the functions after it. So this is why it restarts straight away. So your challenge right now is to delay the execution flow before the level reopens. And you want to delay it by the same duration that it takes to fade the camera out. So pause the video here and give this challenge a go, and then when you're ready, come back and resume the lesson. Okay, so we want to add a delay function after our start camera fade and before the get current level name function. So to do this, we can drag out the output pin of the start camera fade and we can simply type and search for delay, and we'll grab the delay here. Now I said that we wanted the delay duration to be the same duration of the camera fade. Now there's a problem here because if we give the duration of 2 seconds for the delay and the duration of 2 seconds of the start camera fade, we've got the same number in two places. Remember I mentioned about magic numbers in a previous lesson. It's not so much a magic number because we can clearly see what this number does. It's controlling the duration on these functions. But what we really want to do is just have one value controlling the duration on both of these functions. But what if we don't want to clog up our variables tab with unnecessary properties? But we have the option of creating a literal float. If we right click and just type in to the search bar, make literal float, we can grab this function and we can just provide a single value here. Let's give it 2 for 2 seconds. And this return value can be reused in multiple locations. So we can drag it to the duration on both of these, and we don't need to create a variable out of this. Now, if you really want to create a variable, you totally can. I just wanted to show you an alternative here. Now let's come back to our level and hit play. And when we roll off, it does start to fade out now we're using this delay, but it's hard to see because once the fade is finished, it immediately restarts the level and we can see the world again. So what we really want to do to finish this off is to make it so the game fades in at the start of the level as well. So this is the final challenge for this lesson. Your objective is to have the camera fade in on begin play. Before you attempt this, think about where it would be best to execute this. That's the only hint I'm going to give. Remember, you can always use the lecture's discussions in the resources to ask any questions in the community, and you can always post and share your thoughts as to where you think you should execute this camera fade. So pause here for this final challenge, and then once you're ready, come back and hit resume, and I'll walk you through the process. Okay, so let's figure out the best place to fade the camera in when the game starts. There's different places we could do this. We don't really want to do it in the level blueprint because if we had a different level, we would have to paste our code around. So where else could we do this? We could potentially do it on the trigger actor, and that would work, but instead I'm going to have my camera fade in from begin play on the player pawn. And I'm going to do this because it's a very obvious place and it's relating to the player. There's other places you could do it too, such as the game mode, but I'm going to keep it on the player pawn. So we can right click and we can get the player camera manager and we can drag out the return value and we can start a camera fade. Now we want to start the camera fade from black. Remember that 0 is fully transparent and 1 is a fully solid opaque color. So the from alpha is going to be 1, the to alpha is going to be 0, and we could choose a duration here. It could be different. I'm going to use 3 seconds, And I'm going to leave the fade in as black, and we don't need to hold when finished, because once the fade is finished it's going to be fully transparent anyway, so there's no reason to hold the fade. Let's just hook this up to the begin play. And remember, we can always change the length of time it takes to fade out the camera from the level trigger actor blueprint. I'm going to reduce my duration here to about 1 second. And remember to hit compile and save on your actors, and you can always just hit Control, Shift and S to save all. And now let's take a look at what happens when we hit play and roll off the edge. So we've just seen a little camera fade in there as well. Let's try this now if we just roll off. Okay, so we fade out, and we've got this little smooth fading in and out when the player falls off edges now. Okay, so that wraps up this lesson. In the next lesson, we're going to be switching back to developing our collectible crystals. So when you're ready, I'll see you there. Hello and welcome to this lesson, which is all about creating a material. In this lesson, we're going to be creating our first material that has the ability to glow. So for the start of this lesson, I just want to take a few moments to organize our blueprints folder, as we have no organization with these assets here currently. So before it gets out of hand, I'm going to create some new folders. I'm going to start by right-clicking and just creating a new folder, and I'm just going to name this Actors, so we can place our actors in here. Within this folder, I'm going to create some subfolders. So we have our level restart trigger actor, so I'm just going to create a new folder just named level triggers, and I'm also going to create another folder for our crystals, and we're going to call this collectibles. So if you just look next to filters, we have this little button, and when you hover over it, it says show or hide the sources panel. When we click this, we can see the folder hierarchy here, so we can click on blueprints, we can expand actors here as well, and we can simply click and drag the blueprints into the appropriate folder, and we can just hit move here to move them. I'm going to do the same for my level restart trigger actor. Okay, now all we have left is the game mode and the player pawn. So right now I want you to organize your blueprints for your project. Just like I have done, I want you to create a folder for your actors within the blueprints folder. Then create subfolders for your crystal and your trigger actor. Next, I want you to create a folder for your game mode and simply move your game mode into this folder. Then for the final step, create a folder named pawns and move the player pawn into this folder. So pause the video here, organize your folders, and then once you've done that, come back to the lesson so we can continue on with creating our first material. So I hope you've organized and arranged your blueprints into folders now. It makes it a lot easier for us to stay organized as we move forwards. So right now we're going to take a look at creating our first material. We're going to create a material for our crystals, and it's going to glow. To begin this, I'm going to create a new folder, but it's not going to be inside the blueprints folder. I want it to be created underneath content. So to do this, we can right click on the content folder and we can just hit new folder. I'm just going to name this materials. Now to create a material in Unreal Engine 4, we can just right click, and we usually go to blueprint class, but underneath blueprint class we can come straight to material to create a new material. So this is going to be for our crystal. I'm just going to name it M_crystal. Now let's double click on this material to open it. So this is the material editor. It's node based just like blueprints, and it's very powerful. Unreal Engine 4 uses a physically based rendering model, which means that the materials render in a realistic way that can visualize physical properties such as how reflective a surface looks or how metallic it is. I'm providing the link to this documentation page that provides extra detail on Unreal's physical based rendering model. If you scroll further down through this page, you'll find some sliders that show you how different values can affect your materials. So in this material editor, we have these output channels that affect what the material looks like. Base color is pretty straightforward. It provides the underlying color of the material. We can provide vector values here that represent RGB values. As a result, it will allow us to change the color of the material. However, you would also use this channel for a diffuse or albedo texture. Metallic makes your material look more or less metallic, and you can see how different values affect this on the documentation. Specular controls how the material reflects light, and roughness controls how reflective the material is. And again, you can see how the specular and roughness affect materials with the sliders in the documentation link on this lesson's resources. Now there's more channels here to work with as well, but the one we are going to be working with closely and focusing on is the emissive color. The emissive color channel allows the material to look like it's casting light when it's really not. So we have the graph here on the material editor, and there's other things going on around the material editor's interface. On the right, we have this palettes panel, and this displays a list of all the expressions and functions you can make use of in the material editor. On the left, we have the material preview viewport. So this sphere is displaying the current output of our material. It's showing us a live update of what the material looks like. And if we didn't want to preview this as a sphere, we can switch between different preview shapes using these icons in the bottom right corner of the viewport. And finally, just below the preview viewport here, we have the details panel. So we have two simple goals here for the crystal material. The first goal is we want to easily be able to choose a color for the material. And the second, we want to be able to choose how much it glows. So I want you to take the first step to get us started here. Using the palette panel, find an expression called constant free vector. Then drag it on to the graph and plug it into the emissive color output. So pause here and give this a go, and then once you've finished, come back and let's resume the lesson. So on the palette panel, we can find the constant free vector node here. Now I asked you to drag it out onto the graph, but you may have noticed this number on the end of the name here. This is displaying the hotkey for this node. This is telling us that if we hold down number 3 on our keyboard and left click on the graph, it will create this node for us. So this is a constant free vector node. So a constant is just a number that is never going to change over time. But this is a constant free vector. And what this means for us is that it's going to output 3 values from this node rather than just 1. And we can see this here. If we zoom into it, it's displaying 0, 0, 0. But in the way that we're going to use this, this is really showing us the values for red, green, and blue. So this node is actually going to provide us the color for our crystal. Let's plug this into the emissive color output and take a look. So we can see the preview window updating, and it's still black after plugging this in. But we can change this. This is because it's still 0, 0, 0. So to change this color here, or to change the value of the constant free vector, we can select the node and click this bar on the details panel where it says constant, or we can just double click on the big black square here. And this brings up the color picker. And we can use the color wheel. We can click and drag around to change the color. And it looks like we're changing the color here, but we're really not, because it's showing us the previous color here and the new color that we've selected, and we can still see that it's black. All we need to do here is just bring up this value slider on the right to apply more of the color. So you just need to remember to make use of this value slider here. Okay, so choose a color for your crystal. I'm going to choose just a nice bluish color over here, and then hit OK. And we can now see that the preview viewport has updated with the color. Now all that's left for us is to be able to control how much this color glows. And this is really easy to do. Just like in blueprints, we can multiply a float to get a larger value. We can multiply our color here to make it stronger. And the stronger we make it, the more it glows. To add a multiply node, we can right click and we can search for it here. We could use the palette panel, or we can use the hotkey, and it's really simple. For multiply, you can just hold down M and you can left click to add the multiply node. Now we can drag the color into the A input of the multiply, and then we can drag the output of the multiply into the emissive color. Now we're multiplying it by the value of 1 we can see here. So currently we're not adding any strength to it. With the multiply node selected, we can see on the details panel we can change the value of 1 here. If we change it to 5, we're going to get a stronger color. And just look what happens if you set this to 120, for example. You're going to see a really bright glow out of the material. Okay, I'm going to set this back to about 5. And the final thing you need to do is just hit the apply button on the toolbar to apply the material. And this is equivalent to compiling the material. Okay, so once you've decided on the color of your crystal and how much your crystal glows, I want you to have a go at this final challenge. Apply the crystal material to the static mesh components in your crystal blueprint. Then while you're there, add a point light component to the blueprint. And with the component selected, take a look at the details panel and see if you can find where to stop it from casting shadows. So pause the video here and give this challenge a good go, and once you're ready, come back to the lesson and we can wrap this up. So we want to apply this material to our crystal blueprint. So let's head over to our blueprints folder. Let's come inside the actors folder and then the collectibles folder. Let's open up the crystal blueprint. And we can switch to the viewport tab so we can see the mesh here. We want to apply the material to this mesh, but remember we have a top half and a bottom half of this quad pyramid that makes up our crystal. So we need to apply the material to both of these static mesh components. And this is really easy to do. We can drop down the material slot here and we can actually type and search for the name. It was m_crystal. And we can grab that there. And we can even hit the magnifying glass to go where it is in the content browser. And that's done that in the background for us because we haven't docked this next to our level here. But it's brought us back to where the material is. And with it selected, we can select the next static mesh component and just apply the material by using the selected asset from the content browser. Okay, and the final thing to do was to add a point light component. So to do this, we can click the green add component and we can scroll down to where we find lights on here and we can add in the point light. Now we can name this if we want. This is just going to be named crystal light for me. And I wanted you to disable it from casting shadows. Okay, so to do this we can scroll down to where we find the light properties on the details panel and we can simply uncheck cast shadows. And the reason we're doing this is because if the light is inside the mesh or above it, it's going to cast some nasty shadows in our level. If we come back to our level, we can see now that all of our crystals have the materials and point lights applied to them. Now the color of the light doesn't match the material of the crystal, so we can come back to the blueprint and we can change the light color to try and match the same color of the crystal. And while we're here, we can also change the intensity of the light. So I encourage you to play more with your materials and the point lights to try and make a fun looking little collectible crystal. Because in the next lesson, we're going to start taking a look at allowing the player to collect these. So when you're ready, I'll see you in the next lesson. Hello and welcome to this lesson where we are going to add an implementation to our crystal blueprint that allows the player to collect crystals when they get near them. So we're going to start further developing our crystals by allowing the player to collect them as they move throughout the level. To get started, we want to open up our crystal blueprint. Now let's break down what's going on here. We have two static mesh components making up the shape of our crystal. And both of these static mesh components have collision applied to them. You may have noticed by now if you roll into these, they block the player. So what we want to do is make it so when the player rolls close enough to the crystal, it triggers an event causing the crystal blueprint to be destroyed and removed from the level. So to do this, we're going to need some sort of collision event. And we don't really want to rely on the collision of our static mesh components here because we have two of them, meaning we could end up dealing with two separate collision events. So we want to avoid this entirely and just deal with one collision event. So our first step here is to disable the collision of both of our static mesh components. To do this, we can select one and then we can hold down left shift and we can select the other component. So now we have both of these selected and we can scroll down on the details panel to where we have the collision section and we can change the collision preset from block all dynamic to no collision to remove the collision for these components. Let's take a look at the components that will make up our crystal blueprint actor. We have the static mesh components that give us the shape of the crystal, and these static mesh components also have the crystal emissive material applied to them from the previous lesson, making them glow. But even though these meshes glow, they aren't emitting light into the world, and this is why we have the point light component above it, to fake that these glowing materials are actually emitting light. Now, for dealing with the collision, we are going to add a sphere trigger component. If the player moves close to the crystal and overlaps this trigger, they will collect it. So your challenge right now is to add a sphere collision component to your crystal blueprint. And I want you to make this component the root component. So pause the video here and give this challenge a go, and then once you have your sphere collision components as the root component for your crystal blueprint, come back and resume the lesson and we can continue on. Okay, so let's add the sphere collision component to our blueprint. If we scroll down, we can find the collision section and we can choose different shapes here, and one of these shapes is a sphere. So we can select this and we can give it a simple name like collision component. And now we want to make it the root component. To do this, we can click and drag it up onto the default scene root, and now our collision component is the root component for our blueprint. With the collision component selected, we can look over onto the details panel and we can find the shape section here, and we can adjust the radius for it just by clicking and dragging this slider here. Okay, so this is all we need to do with our components here. Let's switch over to the event graph for some visual coding. Let's start by removing the event begin play and also the event tick. So we just have this event actor begin overlap here. So this is the only event we need, and this is going to fire whenever any actors overlap with any of the components of our blueprint. Now remember, the only component with collision here is the collision component, because we've disabled collision on the crystal static meshes, and there's nothing that will cause a collision on the point light component. So this event begin overlap is really only going to fire when an actor enters our sphere collision component. Now remember, this other actor pin on the event returns the actor that caused the overlap. If the player caused the overlap, this pin is going to return the player pawn. So your challenge right now is to check to see if the other actor is equal to the player pawn. And if it is equal, find and call the function named destroyActor. So pause here and take your time to have a go at this. Then once you think you're ready, come back to the lesson and I will walk you through it. Okay, so to do this, we're going to drag out this other actor pin here, and we're going to check to see if it's equal to something. So to do this, we can type in the equal sign and we can grab the equal function. Now we want to check to see if it's equal to the player pawn. So we're going to right click and call the function named getPlayerPawn. And the return value here returns the player pawn. We can plug this into our equal check to check to see if it's the player that has caused the overlap. Now we want to call a function named destroyActor. We can just right click, we can find this function by coming down to the utilities category, and we can just find the destroyActor function if we keep scrolling down. Of course, we can type and search for it if we want to, but this is where this function exists. So when this function is executed, it causes the actor to be deleted from the level. Now we only want to call this function if it's the player pawn that has caused the overlap. So to do this, we can grab a branch. We can hold down B and left click, and we can plug the Boolean return value from our equal check into the condition of the branch. Now we just need to hook up the execution pins. From the begin overlap, we're going to go to the branch, and then we're going to use the true output from the branch to the destroy actor. So this now says if the player pawn has caused an overlap, destroy and delete this crystal from the level, and it gives the illusion that the player has picked it up. So let's come back to our level to test it out. We can hit play, and we can now see that the player can roll into these crystals to collect them. Now this is a very simple system, and we're going to expand upon this over the next lesson. So once you're ready, I'll see you there. Hey, and welcome to this lesson, which is all about blueprint timelines. In this lesson, we're going to learn how we can make an actor smoothly move between 2 points over time. Okay, so our current implementation for the crystal makes it so the crystal destroys itself as soon as the player overlaps with it. Now we're going to make this a bit more fancy. We're going to make it so when the player gets in range of the crystal, it's going to start animating and gliding towards the player over a period of time, and when it gets close enough to the player, it will then destroy itself. So I'm going to break the link to this destroy actor function and just move it out the way for now. Now let's start by taking a look at updating the crystal's location when the player has overlapped it. To update the location of the actor, we can simply use the set actor location function. Now this function only allows us to provide one vector here. As soon as this is executed, it's instantly going to teleport the actor to a new location. But we want it to smoothly blend between two locations, the location of our crystal to the location of the player. So is there a way that we can take this input vector here and do something with it to make it blend between two locations? Well, yes, there is. Our first step here is to call a function named lerp. And we can grab this lerp vector function. This allows us now to provide two vectors instead of just one, and we also have this alpha input. Lerp is short for linear interpolation, which may seem like a scary term, but we're going to start breaking this down. Notice on our function we have a vector A input, a vector B input, and we have a float input for something named alpha. Now let's just imagine we have a line. And let's say that A is the location at the start of the line. And let's say that B is the location at the end of the line. Okay? Now, where does this alpha come into play? Well, the alpha value determines a location along this line. If we provide a value of 0, we would be at location A. If the alpha value is 1, we would land at location B. And if the alpha value is 0.5, we would be halfway between location A and B. Okay, so I think you're starting to get it. The alpha value is returning a location based on our A and B inputs. Now let's look at this in the context of our crystal. If A was the location of the crystal and B was the location of our player, the alpha value would allow us to determine a location between our crystal and the player. Now what we really want to do is make it so we start at an alpha value of 0 and then smoothly animate the alpha to go from 0 to 1. And the result of this would be smoothly blending the location of the crystal to the player's location when called with the set actor location function. So to summarize, with this lerp vector function, we provide two different inputs to the lerp. In our case, we're providing vector A and vector B. And the alpha input value will cause this function to return a location based on the A and B inputs. But if we smoothly animate the alpha value to go from 0 to 1, we would smoothly blend between two locations. Okay, so this all sounds great, but how on earth do we animate this alpha value to go from 0 to 1? Well, this is where blueprint timelines come into play. We can create a blueprint timeline anywhere on our event graph by right-clicking and scrolling all the way down to the bottom of the action menu, and we can click on Add Timeline. Now when you add a timeline, you have to name it. Let's just name ours Alpha Blend Timeline. So a timeline allows you to animate values over time, and to do this we add tracks within the timeline which allow us to keyframe values. Okay, but before we dive into that, I just want to point out the execution pins on the timeline. So we have different pins for playing, reversing, and stopping the timeline, and on the right side we have output pins for updating and finishing the timeline. So the update output will continuously execute while the timeline is playing, and the finished output will execute when the timeline has finished playing. Now let's dive into the timeline. We can double click on it to enter it. A timeline allows us to add different tracks, and we can see the different types of tracks we can add in the top left of its interface. and we can just hover over these and it will tell us what they are. Now, instead of going through all the tracks here, we're just going to focus in on this first track, which is a float track. And a float track will allow us to keyframe and animate a float value over time. But when I say over time, how long do I mean? It could be any length of time. Well, if we look next to where we add in the tracks, we have this length input value here. So this is telling us how long the timeline will play for, and it defaults to 5 seconds. Okay, now let's add a float track. We can click the Add Float Track button here, and this will add it in for us. And it asks us to name the track. Now, what's it going to do? It's going to smoothly interpolate our alpha value over time, right? So we can just name this Smooth Lerp Alpha. To add a keyframe onto this track, we can hold down left shift and left click anywhere on the timeline. And we can forgive ourselves by recklessly placing the keyframe anywhere, because when we have this keyframe selected, we can see the time and value it returns here. So if I wanted this keyframe to be at the start of the timeline, I would change the time value here to be 0, and if I wanted it to return the value of 0, I would click the value here and just type in 0 again. Okay, and we can add more keyframes just by holding down left shift and left clicking anywhere, and we can see when we add additional keyframes, we can see a line showing us that this value will be animated over time. So your challenge right now is to set your timeline to be 0.68 seconds in length, and then on your float track, add a keyframe at the start of the track and set it to have a value of 0. Then add another keyframe at the end of your track with a value of 1. Okay, so pause here, and then once you set your timeline length and keyframes, come back to the lesson and we can continue. Okay, so I'm going to start by changing my timeline length to 0.68 seconds, because we want the crystal to move towards the player pretty quickly when they get close to it. Now we need to set the keyframes so we can animate a value going from 0 to 1 for the duration of the timeline, and this will be used for driving the alpha of the lerp. So we can add 2 keyframes. We can do this just by holding left shift and left clicking on the track here. We can do that once and then we can do it again. So now we have 2 keyframes. With the first keyframe, I want to set its time to 0, so it's at the start of the track, and we're also going to make it return the value of 0 as well. And with the second keyframe, we can select this, and we want this to be at the end of the track. So the time for the end of the track is going to be the same as the length of the timeline. Okay, so it's going to be 0.68. And then we want this to return a value of 1. And if we zoom out, we can see that we now have this simple linear curve going on here. Okay, if we hover over this, we can see what happens over time. We can see that the time increases and the value increases as well. And we can see it's going from 0 to 1 over time. So this is exactly what we want to drive the alpha on our lerp. Let's come back to the event graph, because this is all we need to do here. Now notice on the timeline we have a float output pin for the float track we just created, and we can now plug this straight into the alpha of the lerp function. Okay, we can hook up the update to the set actor location, and now the timeline now provides a way for us to smoothly animate the alpha between 0 and 1. Now we don't have any vectors going into here yet, so we currently don't have any locations to interpolate between, but I want you to have a go at finishing this off. Promote the vector A input of the lerp to a variable and name it lerp start location. Remember, you can promote pins to variables by right-clicking on them. For the vector B input, we want it to use the location of the player pawn. And then for the final step of this challenge, see if you can figure out how to execute the destroy actor function when the timeline has finished. So pause the video here, and then once you finish this challenge, come back to the lesson and we can continue on. Okay, so to get started here, I'm going to make a little more space with my nodes, and we are working with the vector A input to start with. Now I said I wanted you to promote this to a variable named lerp start location. So we can do this by right clicking on the pin here, and we can select promote to variable, and we can simply name this lerp start location. Okay, so we have our vector A input. Now for the vector B input, I told you to get the location of the player pawn. To do this, we can simply right click, we can call the get player pawn, and with the return value here, we can drag this out and get the actor location. And we can use this as the B vector input. And now we have our destroy actor function on the end here, and we want to call this when the timeline has finished. So to do this, we have the finished output on the timeline. We can just move our destroy actor function over here, and we can connect the finished output pin to the destroy actor. So when the timeline finishes, the actor will be destroyed. And in the case of our game, this means that once the crystal has reached the player, it will destroy itself, making it look like the player has collected it. Now let's play the timeline once we know that the player pawn has overlapped the crystal's collision component, or just overlapped with the crystal. So to do this, we can drag the true output from the branch to the play on the timeline. Okay, now let's come to the viewport and let's increase the size of the collision component. We can do this by selecting it, and then on the details panel we can increase the sphere radius size here. Now let's come back to our level and hit play to take a look at what happens when we roll near a crystal. We can see that it's certainly gliding and smoothly moving towards the player, but it looks like it's starting from a strange location. And the reason this is doing this is because we haven't set a value on our lerp start location. If we select it, we can see that the start location is 0, 0, 0. So basically it's always interpolating from wherever 0, 0, 0 is of our level and moving towards the player. Now we want the start location to be the location of the crystal. So what we're going to do is just move our timeline and the rest of the nodes here just across slightly, and we are going to drag out the lerp start location, and instead of getting it, we are going to set it. We're going to connect the true of the branch to this because we're going to set the lerp start location before we play the timeline. Now what do we want to set it to? Well, we want to set it to the actor location of the crystal. So we can simply right click and type in get actor location, and we can plug this into the set of the lerp start location. And now if we come back to our level and hit play and roll towards our crystal, we can see that it's smoothly moving towards the player. Now in the next lesson, we're going to start cleaning up the blueprint more and also adding a little more polish by taking our first look at blueprint functions. So once you're ready, I'll see you in the next lesson. Hey, and welcome to this lesson where we're going to cover encapsulating parts of your code into blueprint functions to help make your code easier to read and also to keep it organized. So in the previous lesson, we set up our crystal blueprint to smoothly move towards the player over time. Now, the code we've implemented into our crystal blueprint class is getting a bit crazy. Visually, it's becoming hard to read due to the amount of nodes and wires we are using. Now, we want to start working and thinking about our code on a higher level. When we view our code, we want to clearly be able to read it and understand what it does. To help us do this, we are going to be encapsulating parts of our code into blueprint functions. By encapsulating code into functions, we are making use of a core principle of object-oriented programming, which is encapsulation. To encapsulate is to show or express the main idea of something in a brief way. You've been using code that is encapsulated in functions this whole time you've been developing in blueprints. You've been using blueprint functions. Let's take a look at a single blueprint function to help break the concept of functions down. The first thing to point out is that we know we are dealing with a function in blueprints when we see this f on a blueprint node. When we look at a function in blueprints, we don't see the function's implementation, meaning we don't see the nitty-gritty details of the code that makes up the function. This is because the code is encapsulated within it. So a function is a collection of code that performs a task. Functions can be named, And by naming functions, we clearly state what the function's task is. And functions are reusable. We can place them and use them as many times as we want in our event graph or even inside other functions. And functions have input parameters, and by using these parameters, we can affect the function's task. And functions can also return values. Now let's take a look at our code that is called after the update output of the timeline. This code here is performing a specific task. It's moving the crystal towards the player pawn. Now when we view our code at the top level in the event graph, we want to clearly read that it's performing this task of moving towards the player pawn. And we can do this by encapsulating our code into our own blueprint function. So we want to start by selecting all of the nodes that perform this task of moving the crystal towards the player pawn. This is going to be everything after the timeline, but just make sure you don't select this destroy actor node here because this is performing a different task. So we can just go ahead and move this destroy actor node up out of the way. So let's select all of these nodes that perform this task. And now let's take a look at encapsulating them into a function. To do this, we can right click on one of the functions we have selected and we can come down to where it says organization and we can collapse it into a function. And now we have to name it, and we can see that has been added to the function section of the My Blueprint tab. So what is the name of this function? What is its task? Well, it's moving towards the player, so let's just call this move to player. Okay, so now we can see on the graph that all our code has disappeared and we are just left with this node here. So this is our function. And we can see that it's already added an input parameter for us onto the function that's already connected to our timeline. And we can't see the code that we had before on the graph because it's encapsulated in the function. So how do we view the code now? Well, we just double click on the function to enter it. So looking inside this function, we have this purple node, and this is the function entry node. This is where our function starts, and it's also where we can read and use our input parameters. If we want, we can clean this up a bit just by moving this entry node up a little, and it just allows us to read this a bit easier. So we can see that this function entry node is connected to the set actor location and the rest of our code here. So this is where our code now exists. Now let's come back to the event graph, and we can see here that this is looking a lot more tidy and it's a bit more clear when we read it. Now let's just look before the timeline where we get the actor location and store it as a starting location. We could also clear this up. I want you to encapsulate these nodes into a function. The name for this function is going to be store starting values. So pause here and encapsulate these nodes into a function, and then once you've done this, let's resume and take a look at the result together. Okay, so we know that we can encapsulate our code into blueprint functions by selecting nodes, and then we can right click on one of the nodes we have selected and we can collapse it to a function. Now the name of this function is going to be store starting values. We can move this along and just make it straight on the execution flow here, and we can double click to enter the function and view its implementation. And we can just move the entry node just to make it a bit clearer when we view the code. Now in the next lesson, we're going to be adding more to this. We're going to be storing more starting values, and we're also going to be doing more with the timeline. But now looking on our event graph, we can see that the code is becoming much clearer to read. And one final thing we should do before moving on to the next lesson is just make sure that the game is still working as expected. And it totally will if you followed along closely, because when you encapsulate code into functions, it's not going to change any of your code. But by thinking of parts of our code as tasks and encapsulating them to make our code easier to read, we're starting to work and think on that higher level. Okay, so when you're ready, let's move on to the next lesson. Hey, and welcome to this lesson where we're going to be making use of multiple blueprint timeline tracks to make our crystal collection behavior a bit more interesting. Okay, so we're going to make a couple more things happen while the crystal moves towards the player pawn. While the crystal moves towards the player, we're also going to make the crystal scale down and also make its point light component change intensity. Now in the previous lesson, we made our code easier to read by making use of these blueprint functions. And looking at our timeline, I'll admit I could have named this better, and it's always important to name correctly. Instead of this timeline being called Alpha Blend Timeline, which is not a great name, we could rename this to something better. To rename the timeline, we can select it, and we can press F2 to rename it. Let's rename this to Collection Timeline. And the track we added to the timeline, named Smooth Lerp Alpha, could have a much better name too. So to rename this, I'm going to enter the timeline by double clicking on it, and I'm just going to select the track, and to select it I can just left click next to the track on the left, or next to the graph editor on the left, and you should see it go orange, and then you can just hit F2 to rename it, and we can name this Collection Progress. Now let's take a look at making this crystal actor scale over the duration of our timeline. The first step here is to store our starting scale for the actor. And we already have a function here called store starting values. We can enter this, and we can actually extend this function a bit here. We can store the actor scale in here. To do this, we can simply right click, and we can type in get actor scale. And the one we're looking for is the function named getActorScale3D. With the return value here, we can right click on this to promote it to a member variable for our blueprint, and we can just call this start scale. And we can hook this up with the execution pins with the lerp start location. And just to be consistent, we can actually rename this variable here. We can select it, and on the details panel we can just take out lerp and we can just leave it as start location. Now we can come back to our event graph, and we're going to be looking just after our timeline now, but I'm going to make you do the rest here. Interpolate your actor scale from your start scale variable we just created and make the scale interpolate to 0. And make sure to make use of the collection progress value on the timeline. Then encapsulate your code into a function and name the function scale crystal. So pause the video here, and if you get stuck, make sure to check out your move to player function because it's going to be very similar. So once you complete this challenge, come back to the lesson and we can continue. So to do this, we want to set our actor scale. So we can right click and we can call the set actor scale function, and we're going to grab the set actor scale 3D. We're going to hook this up next to the move to player function. So remember, it's coming off the update of the timeline. The timeline is going to update, and it's going to move the crystal to the player, and it's also going to set the scale of our crystal. Now, what do we want to set the scale to? Well, we want to interpolate it. So we're going to drag out this input vector, and we're going to type in lerp. And we're going to grab the lerp vector function here. Now we want to interpolate from our start scale variable we just created. So we can grab that off the variable tab, and we can plug this into the A input. So it's going to interpolate from the start scale, and we want it to, we basically want it to shrink entirely. So we don't even have to put in any values into this B input because this is zeroed out completely. It's going to make our scale go from whatever the actor scale is to 0. But to animate it smoothly scaling down, we need to make use of this collection progress return value on the timeline. Okay, and that's all we need to do for this little task here. We can actually select all the nodes, and then we can right click on one of them, and we can encapsulate it by collapsing it down to a function. And we can name this scale crystal. Now let's take a look at what happens when we come back to our level and hit play. We can see that when we roll towards these crystals, they are moving towards the player, but they're also scaling down over time. Okay, great. So let's just come back to our crystal blueprint because we're not quite finished yet. Now the alpha of our scale crystal is coming from the same collection progress return value on the timeline. But there's no limit to how many tracks we can add to a timeline. So we can add another float track if we want to, and we can call this scale progress. And we can hold down left shift and left click to add keys, just like we did above. We can set the time and the value from them. We can add another one. We can set that to the length of the timeline, which is 0.68 seconds. And we can set the value to 1 as well. So we've got the exact same float track as above. Now remember, the first keyframe means that we are at the starting scale of the actor, and the final keyframe, if it's at the value of 1, this means that it's going to be all the way on the B input of our lerp here, okay? So it's going to be, the value of 1 is going to be equal to the actor having 0 scale, so it's going to be completely shrunk down, invisible. But just like there's no limit on how many timeline tracks we can add, there's no limit on how many keyframes we can add here. We can create some pretty interesting behaviors in relation to scaling our crystal just by adding another keyframe. Now, what happens if this keyframe outputs a negative value? Well, this would mean it would actually increase the actor's scale. Looking at this lerp diagram here, we can see that if you move from A closer to B, we would be scaling the actor down, but moving from A away from B, we would be returning larger values, and as a result, we would start scaling the actor up. So I really encourage you to experiment with these keyframes and do share your results in this lecture's discussions on the Resources tab. You can see my results here. When I collect my crystal, it inflates a little and then deflates at the same time as moving towards the player. Okay, so right now I have a final challenge for you. Create a new timeline track named Light Intensity and store your starting light intensity. Then interpolate your light intensity to 0. And of course, make sure to encapsulate your code and name the function adjustLight. So have a go at this final challenge, and I really encourage you to experiment with the timeline, and then once you're ready, come back and we can wrap up this lesson. So I've created my timeline track, I've named it light intensity, and I've added some keyframes, and you can see I've got a bit of a zigzaggy pattern going on here. Now, back in the event graph, I want to start by storing my light intensity. So I'm going to come inside the store starting values function, and we can grab the crystal light component, we can drag it out, and we can get its intensity. And we can promote this to a variable. And we can just name this start light intensity. And we want to make sure we hook it up to the execution pins and make it straight on the execution flow there. So that's looking good. We can come back to the event graph, and now we can take a look at interpolating our light intensity. We'll start by grabbing the light component, and we want to call the set intensity function. We can hook it up to the execution pin here, and with the intensity, we want to interpolate the value. So we can drag it out, and we can type in lerp and get the lerp float function. And this works the exact same way. We can grab the light intensity from the collection timeline, and we can plug that into the alpha. The A input here is going to be our start light intensity, and the B input is going to remain at 0. Okay, so we're going from the starting light intensity, whatever that is, and that is about 20,000 units here. So we got the scale of going from 20,000 units to 0 on the lerp. Now we would want to take a look at encapsulating this code here. So we can just select all the nodes, select one of the nodes and collapse it down to a function, and we can name this adjustLight. Okay, so I think this is looking good. Let's come back to our level and let's hit play and let's see what happens. So we can see that the light starts blinking, it starts scaling up and down, and it's also moving towards the player pawn. Okay, so this is looking really good. Now looking at our code, the only final thing I'm not happy with here is just this get player pawn and this equal operator and this branch here. But this branch has 2 output execution pins, and we can't make a blueprint function return multiple execution pins. So in the next lesson, we're going to be taking a look at a solution for this. Hello and welcome to this lesson, which is all about blueprint macros. We're going to use blueprint macros as a replacement for a function because it allows us to work with additional execution pins. So looking at the blueprint code for our crystal blueprint, we can start to see that it's becoming a lot clearer to read because we've encapsulated a lot of our code down into functions. Now, the only thing we're not really happy with is where we do this equal check from the overlap. Okay, so something overlaps with the crystal and we check to see if it's the player pawn, and if it's the player pawn, we then continue on executing our blueprint code. But there's a problem here. The branch has two output pins. It's returning two output execution pins, but functions can't have multiple output execution pins. So if we can't collapse these down to a function, we need a solution. Is there something that we can do to collapse these down into a node that's similar to a function? Well, yes, there is. We can use blueprint macros. So we know that blueprint functions can have input parameters, and blueprint functions can return values as well. But blueprint functions cannot have multiple input or output execution pins. So we're going to have an issue here if we want to collapse this code down into a function, because it returns two output execution pins. And this is where blueprint macros come in handy, because blueprint macros can have as many input or output execution pins as we want, and we can even name the execution pins. So to create a blueprint macro, we can look towards the My Blueprint tab, and we can come down to the macros section, and we can add a new macro here. Let's name this macro isPlayer. Now looking on the details panel, we can see we can add inputs or outputs, and currently our macro has no input execution pins or output execution pins. So to add a input execution pin, we can hit new parameter, and look, it's already given us the execution pin type here, and we can give it a name. We could just name this execute. And we need to add another input parameter because we need to check an actor and compare it to see if it's equal to the player pawn. So we can drop down the type here and we can search for actor. And we want to grab the actor object reference, and let's give the input parameter a name. Let's just name this actor. And now I'm going to challenge you to finish this macro off. Create two output execution pins on your macro. Name the first output isPlayer, and then name the second output notPlayer. And for the final step, add your compare code to this macro. So the code where we compare the other actor to see if it's equal to the player pawn, and where we use the branch, we want to add this code to this macro. Okay, so pause here, and once you finish this, come back to the lesson and hit resume. Okay, so to finish this macro off, I'm going to add a new output pin. I'm going to make sure it's an execution output pin, and I'm going to name this isPlayer. I'm going to add an additional output pin, and this is going to be notPlayer. So we have two outputs on this macro now, one for if it's the player and the other for if it's not the player. Now we need to add the code into this. We've already got the code in our event graph here, so we can just select all of this. We can hit Control X to cut it, and we can come into the macro and paste it in. Now we can just move and organize our nodes here just to make it a bit neater. So we've got this input actor pin. This can go straight into the equal check here, and we want to make sure we hook up the entry node to the branch, and then the true output for the branch, if it's the player, it's going to go to the isPlayer output, and if it's not the player, it's going to go to the output named notPlayer. Okay, and that's all our code in our macro here, and then we can drag the macro onto the event graph, and we can hook up the execution pins and just make sure we input the other actor from the begin overlap event into this, and then the isPlayer output is going to go to the store starting variables. So something causes an overlap with our crystal. Is it the player? And then if it is, continue on with our collection code. And we can see that it's a lot easier and neater to read now. And if we come back to our level and hit play, we can see it still works just as expected. Okay, so that wraps up this lesson on blueprint macros. We can see how encapsulating our code into macros can be helpful if we require additional execution pins. And if you had any additional questions or wanted to showcase your work up to this point, I encourage you to use this lecture's discussions on the resources tab for this lecture. Okay, so in the next lesson, we're going to step away from our crystals to create some projectiles that will cause damage to the player. So when you're ready, I'll see you there. Hello, in this lesson we are going to start creating a projectile actor that's going to be used as a projectile that will be continuously fired from a cannon that we're going to be building in a separate lesson. Okay, so we're going to start this lesson by creating a new actor. Let's come inside the blueprints folder and then inside our actors folder. Inside here, let's create a new folder and let's name this Projectiles. And then inside this folder, let's create a new blueprint class and let's make it an actor and let's name this BP underscore projectile. And let's open up this blueprint. Now let's take a look at the components that we're going to need for this projectile. Our projectile class is going to be fairly simple. We're going to need a sphere collision component, and this is going to be the root component. And then we need a static mesh component, and we're going to assign a sphere mesh to it. And we're also going to add a new component that we haven't taken a look at yet, and this is the projectile movement component. The projectile movement component allows an actor to continuously move like it's been shot from a gun or from a cannon. So your challenge right now is to add these components, and with your static mesh component, when you assign the sphere mesh, make sure to assign a material to it as well. So pause the video here, and then once you've added your components, come back to the lesson and we can carry on. Okay, so let's add in our collision component. This is going to be a sphere collision. We can name this collision component. And we want to make this the root component. So let's click and drag it up onto the default scene root to make it the root. Now we want to add in a static mesh component, but we also want it to have a sphere mesh applied. And there's a trick here. We can add in a new component and we can just grab the sphere components here. This is actually a static mesh component, but it automatically applies a sphere mesh to it. Let's just call this mesh. Now, let's scale this down so it's a bit smaller than our collision sphere here. We're going to disable the collision of this mesh because we don't need it, because we're going to make our collision component handle all the collision for us. And of course, we want to apply a material to this. I'm going to come back to the starter content and then inside the materials folder, and I'm going to select one of these materials. I'm going to grab the metal gold, and I'm going to maximize this and just assign it by using the selected asset from the content browser. And the final thing we need to add here is the projectile movement component. We can add a new component and we can just type in projectile and we can grab the projectile movement just there. And if we select the projectile movement, we can see all the properties for it on the details panel. Now there's quite a few different properties on the details panel for this projectile movement component. We're just going to focus in on the projectile section, and we're only going to use two properties here. The first property is the initial speed, and this is in centimeters per second. And the second property is the projectile gravity, and we're going to disable the projectile gravity because when our projectile moves throughout the world, we don't want it to fall or dip over time. So I want my projectile to move throughout the world at about 5 meters per second. So I'm going to change the initial speed here to 500. And we want to disable the projectile gravity. So we can take the projectile gravity here and we can change it to 0 to disable it. Now let's come back to our level and let's drag out our projectile blueprint into our level. Now we want to play the game and see the projectile moving, but we don't actually have to hit play. We can drop down the arrow next to play and we can hit simulate. Simulating the game runs the game as if it's playing, but we don't have to possess a pawn, so we can still move around the editor as usual. So when we simulate the game, we see the projectile is moving. Let's rotate the projectile because we're going to be using the projectile kind of going from one wall to the other. We're going to use it as kind of like a blockade for the player that they have to pass. But notice if the projectile keeps going, it's going to go past the wall, it's actually going to go through the wall, and it just keeps continuously going. So I have a challenge for you right now to fix this. Your collision component is currently set to only overlap actors, so I want you to change the collision preset to block all, and then add some blueprint code to destroy the actor when it hits something. So pause here and give this challenge a good go, and then when you think you're ready, come back to the lesson and we can continue. Okay, so our first step here is to select our collision component, and we're going to change its collision preset from overlap all dynamic to block all. Now for the blueprint code, there's two different ways we could create an event that's generated when this actor hits something or when our components hit something. We can scroll down when we have the component selected and we can grab an event from here. There is an on component hit event that we can add. Or we can come into the event graph, we can right click and we can type in event hit and we can get the event hit just here. So we're simply going to hit something, we can drag this out and call destroy actor. So now when the projectile collides with something, our event here will execute the destroy actor function, making the projectile disappear. So let's come back to our level and see the result when we simulate. We can see that the projectile disappears, and if we pay close attention to the world outliner, we can even see it gets listed as a destroyed actor. Okay, so this is a very basic projectile we currently have, but in the next lesson, we're going to start creating our cannon that's going to continuously fire these projectiles. So when you're ready, I'll see you in the next lesson. Hey, and welcome to this lesson where we're going to learn how to import 3D models that are in an FBX format into Unreal Engine 4. We're also going to use these models to create our cannon actor. Okay, so we need a good visual representation of our cannon. So in order to achieve this, we are going to be importing some custom 3D models. Let's start by creating a new folder in the content browser called Meshes. And inside this folder, we want to create a subfolder called Cannon. And inside this Cannon folder, we can import our meshes. Now, I already have the Cannon meshes on my machine here. And these files are in an FBX format. FBX is an acronym for Filmbox, and this is one of the main formats to use when importing meshes and models into Unreal Engine 4. So I want you just to pause here for a moment and navigate to the Resources tab for this lecture on Udemy. On the Resources, you'll find these two models that you can download. So pause here, download them onto your machine, and then let's continue. So with your Cannon models downloaded, we can add these to our project by selecting both of them, and we can click and drag them into the content browser in Unreal. And when we release, it brings up the FBX import options. Now there's many import settings here that can be adjusted to affect how a model is imported, but we aren't going to be going through each and every one of these settings right now. We just want to focus on getting our Cannon into Unreal. Luckily, all of these settings are good to go, just apart from two. And we don't want to create any unnecessary assets when importing these models. So before importing, the two settings we want to turn off or uncheck are the import materials and import texture settings. Just make sure these two are not checked. To import a model, we can hit import, but remember we're importing two separate files here. We're importing two models. We want to hit import all and use these import settings for both of the models. So your challenge right now is to import the Cannon FBX files into Unreal, and when importing these files, make sure to uncheck import materials and textures. So pause here, and once you have your FBX files imported, we can continue on. Okay, so I'm going to hit import all. So once imported, we can see that they are static meshes, just like how we've been using throughout this course. We have the Cannon base, and we also have the Cannon that will sit in the base. So even though these are separate assets, these two meshes share the same pivot point. If we select both meshes and drag them out at the same time, we can see that they come out into our level connected. Now these assets have no default materials, but we can use the starter content to apply some default materials to them. Let's open up one of the meshes. Let's start with the Cannon. With the mesh open, we can see the material slot here, and we can type and search in this filter for some materials. I'm going to search for metal, and these are the metal materials from the starter content. For the Cannon, I'm going to grab the chrome material, and for the Cannon base, I'm going to grab, see what metal we can grab here. I'm going to grab the burnished steel. Okay, we can close this and we can remove our projectile here. And we can see the results of our cannon here now with the materials. So I encourage you to try different materials for your cannon and make sure to share the results in this lecture's discussions that you can find in the resources tab for this lecture. But right now, I have another challenge for you. I want you to create a blueprint actor for your cannon. Add the 2 meshes we imported as components for the cannon and make sure to make the cannon base mesh the root component. So pause here and create your cannon blueprint. Then once you've done this, we can continue. Okay, so I want to remove these static meshes I dragged into the level because I'm going to create a blueprint for our cannon. We can come to the blueprints folder, inside the actors folder, and we can create a new folder here named cannons, or just cannon. Inside this folder, we can right click and create a new blueprint class, and we want it to be an actor. And I'm just going to name this BP underscore cannon. And let's open up this blueprint and let's add the static meshes to it. I'm going to add a new component. It's going to be a static mesh component. And this is going to be the cannon base. And I also want this to be the root component. So I'm going to click and drag it up onto the default scene root. Now with the mesh selected, I can drop down the static mesh slot and I can choose the cannon base to assign it there. And I'm also going to add in another static mesh component. And this is going to be the cannon itself. And we can see it's already a child of the cannon base because the cannon base is the root component. So the cannon is going to be our cannon static mesh. And this is looking good. We can hit compile and save here and close this. And we can drag our mesh onto the wall. And this is what it's going to look like. We can hold Alt and we can click and drag to duplicate. We're going to be placing some cannons across our walls here. So that wraps up this lesson. We now know how to import FBX files into Unreal Engine 4. In the next lesson, we're going to be making our cannon start firing our projectile actors. So when you're ready, I'll see you there. Hey, and welcome to this lesson, which is all about spawning actors at runtime. At the end of this lesson, we will end up with our cannon actor spawning our projectile actors repeatedly. So in the previous lesson, we imported some 3D models and we used these to create a blueprint actor for our cannon. Now we want to take a look at how we can make our projectiles spawn from this actor. One of the first things we need to decide is where we would want our projectiles to spawn from. We want our projectiles to spawn at the end of the cannon's barrel. So how do we mark a spawn point of sorts inside this actor? Well, there's different ways we could do this. We could just use a scene component and move it to the end of the cannon's barrel, but I really want us to clearly understand the orientation of our spawn point. So let's add a arrow component. And let's name this projectile spawn point. And let's make sure that this arrow component is a child of the cannon. So the arrow component is just like a scene component really, but it has the benefits of rendering an arrow, so we have an idea of orientation. Also, arrow components are hidden in game by default. If you were to play the game, you wouldn't see it, and they also don't have any sort of collision that we have to worry about. So a quick challenge for you right now. I want you to adjust the arrow's location and orientation so it sits at the end of the cannon's barrel and also points in the same direction of the barrel. You can also adjust the size of the arrow and even its color in the details panel when you have it selected. So make sure to explore these settings. Okay, so pause here, and then when you have your arrow component set up, let's continue. Okay, so I'm going to select my arrow component, I'm going to rotate it and then translate it to the end of the cannon's barrel to about where I want the projectile to spawn. Now with the arrow selected, we can see on the details panel that we can adjust the arrow's size and we can also change the color to any color that we like the arrow to be. Now let's switch over to the event graph to begin coding the cannon's behavior. When the game starts, we want the cannon to wait for a short period of time, and then we want it to spawn our projectile actor class. And we also want to animate the cannon mesh to make it visually look like it's firing. And then we want this whole process to repeat. So to start, we're going to drag out from event begin play and we're going to call a delay. The duration of the delay is going to be the cannon's fire rate. If we put in 1 second for the duration, it's going to fire every second. Now we want to spawn our projectile class. So how do we do that? How do we dynamically spawn an actor at runtime in Blueprints? We haven't taken a look at this yet, but it's really easy to do. We can open up the Blueprint action menu and we can scroll down to the game section, and if we scroll all the way down on the game section, we can find spawn actor from class. So this node allows us to spawn actors dynamically at runtime. It may look a bit overwhelming at first if you've never used it, but it's really straightforward. We choose which actor class we want to spawn with this class drop-down selection here. We choose where we want the actor to spawn in the world with the spawn transform, and remember, you can split the transform pin to gain access to the location, rotation, and scale. And we also decide how the actor spawns if it detects its spawn point is colliding with something. And this is something to think about here because our projectile might be quite large when it spawns and it might be colliding with our cannon mesh. So we may need to make some adjustments. And then we have the return value, which simply returns the actor that gets spawned. So I have a challenge for you right now. Using the spawn actor from class node, spawn your projectile class. And for the spawn transform, use the world location and rotation of your projectile spawn point. And don't worry about the scale for now. And then loop the execution flow back to the delay. So pause here and have a good go at this challenge, and then when you're ready, come back to the lesson and we can continue on. So I have selected my projectile class using the class drop down on the spawn actor node, and I have my projectile spawn point, the arrow component. I have its world location and its world rotation that I can use for the spawn transform. I'm going to right click on the spawn transform and split it to gain access to the location, rotation, and scale. We can plug the world location of our spawn point into this and the world rotation into the transform rotation there. Now with the scale, I'm going to leave this at 1, and the reason I'm doing this is because I don't want the scale of the arrow components to decide the scale of my projectile. And with the collision handling override, we're going to leave this on default, but I do know that my projectile is probably going to be too large to spawn, and the projectile will be colliding with our cannon. For now, I'm going to select the cannon mesh, and I'm going to remove the collision. I'm going to drop down the collision preset here and change its collision to no collision. And the final step here is just to make this code that we have here loop. We can drag out the output execution pin of our spawn actor node, and we can scroll all the way down to the bottom and we can grab the add a reroute node. So this is just a nice easy way of rewiring our blueprints here. We can drag this all the way to the delay, and we can double click on a wire at any point to create these reroute nodes. Okay, and that just allows our code just to look a bit neater for now. Okay, great. So let's check out the result of this. We can hit compile and save. We can come back to our level and we can hit simulate. We can use the hotkey for simulating, which is Alt S. So we can delay for a second, and then we can see that our projectiles are now spawning out of our cannon. So it's working, but we can see that the projectiles are still kind of large. But in the next lesson, we're going to take a look at exposing a property that allows us to adjust the scale of our projectiles and also the fire rate of the cannon itself. So when you're ready, I'll see you in the next lesson. Hey, and welcome to this lesson, which is all about exposing blueprint variables. By the end of this lesson, you will have learnt how to organize your variables better and also expose them directly to an actor's details panel when you select them in your level. Okay, so inside our cannon actor, we're spawning our projectiles every second at our projectile spawn point. We're going to take a look at a way we can easily control the scale of the projectiles that are fired from the cannon. We're going to start by creating a new variable, and we're going to name this projectile scale. And the variable type is going to be a float, not a vector. We can see on the spawn actor node that the spawn transform scale is a vector, but our projectile scale is a float. But look what happens if we click and drag it and connect it to the scale. It says it's not compatible with it because it's not a vector. But if we drag it onto the event graph and just hit get and connect this to the vector, it will convert the float to a vector. So what is this conversion really doing? Well, it takes whatever the float value is and it applies it to a vector uniformly, meaning if our float value was 0.75 as an example, the vector output value would be 0.75 for the x, y, and z values. And we can also see this explained when we hover over this node here. So I'm going to hit compile, I'm going to select my projectile scale, and I'm going to give it a default value of 0.6. Now we can close out of here and we can hit simulate, and we can see now that the projectile is a bit smaller than it was before. Okay, but what if I wanted to make the scale of the projectiles coming out of one cannon, like this cannon here, larger than the cannon next to it? How could we do that? Well, we could do this by exposing our projectile scale variable. Exposing variables is great for level design. When you expose a variable, it makes it visible on the details panel when you select an actor in a level. Adjusting exposed variables from the details panel only applies to the actor instance you have selected. And in the case of our cannon, it allows us to independently set different values for each cannon instance we've placed in our level. So how do we go about exposing a blueprint variable? Well, there's two ways that we can do this. We can look towards the My Blueprint tab, and where we have the variable, you'll notice this icon on the end of the variable name. So this is actually a closed eye, and we can click this to toggle it, and it opens the eye here. We can see the icon updates, and this means that the variable is now public, it's now exposed. And there's another way we can do it. We can simply select the variable, and we can see on the details panel we have this instance editable checkbox. Okay, and when we toggle this here, it also toggles the eye icon there as well. So they do the same thing there. So with it exposed, we want to compile our blueprint. Let's come back to our level and let's select a cannon actor, and we can see on the details panel that we have our projectile scale exposed here. If we change this value, it only applies to this cannon actor. This other cannon actor here, just next to it, has the default value. Okay, so we can independently set these values for each cannon if we want to. Okay, so it's a pretty powerful feature, and right now I want you to attempt exposing your own blueprint variable. The delay function that we've used in our cannon actor represents the fire rate for the cannon. So right now I want you to create and apply a variable for the cannon's fire rate. And I also want you to expose this variable. So pause here, create and expose your variable, and then once you've done this, come back and resume the lesson. Okay, so we want to create and expose a variable for our cannon's fire rate. I'm just going to remove these two other events because we don't need these right now. And I'm going to zoom into my delay function, and with the duration parameter, I'm going to right click on this and promote it to a variable. And this is going to be the cannon fire rate. Now we can expose this variable by using the details panel, or we can just open the eye on the My Blueprint tab for it. Now let's hit compile. And if we come back to our level, we can see that if we select any of our cannons, we now see a cannon fire rate for it. We can independently change the fire rate for each cannon in our level. And by doing this, we can see that if we simulate, our cannons are now firing at different speeds. But if we select a cannon, we can see on the details panel that our variables are in a category named default. And we can type in any value into these variables. So if we wanted to put -5,000, we're allowed to do so. But what if we didn't want that to happen? What if we want to restrict how people use our blueprints? So let's think of this in the standpoint of working with a level designer. As the blueprint programmer, you may want to expose properties to level designers that they can use for the cannon, but you might want to restrict them on which values they can use. And we can do this by coming back to our cannon blueprint, and if we select a variable, we can see on the details panel that we have this category section here. It says here that editing this will place the variable into another category or create a new one. So we can simply select where it says default, and we can create a new category just by typing in a name. We can call this cannon properties, and we can see when we do this on the My Blueprint tab, we have a cannon property section now. The projectile scale isn't in this yet, but we can click and drag it up and drop it into the section as well. Now to restrict values, we can select a variable, and on the details panel, we can see we have this slider range and value range here. So values will be clamped to this range. So if we put this value of 0.5 and 2 seconds, this would mean that our exposed fire rate will never be able to go outside of this range when we type values in on the details panel. And we could do the same with the slider, which allows us to clamp the slider range. We want to make sure we do the same with the other variable we have here, which is the projectile scale. Now when we come back to our level, we can see that our variables now have a clamped range, and they are also organized in a category named cannon fire properties. So the result of all of this allows us to have much more control over our variables, but by exposing them, we open up lots of dynamic gameplay options where we can have different behaviors for each actor. Now we're nearly there with the cannon. In the next lesson, we're going to be finishing off the firing behavior by animating the cannon mesh to make it visually appear like it's firing. So when you're ready, I'll see you in the next lesson. Hey, and welcome to this lesson where we're going to learn about animating meshes with timelines. By the end of this lesson, you'll have learnt how you can move meshes with timelines, and also how you can add execution pins to timelines by using event tracks. Okay, so when our cannons are firing, we can see that the cannon barrel doesn't actually move. So we're going to make use of a timeline to animate the cannon when it fires. To do this, we're going to animate the relative location of the cannon barrel mesh. Let's go inside the cannon blueprint and inside the viewport for it, and let's select the cannon mesh. We can actually rename this static mesh component to cannon barrel, just to be more consistent there. So remember when we view the transform on the details panel that this isn't the world location. This is showing us the transform relative to the cannon barrel's parent, which is the cannon base. Now let's imagine this barrel animating for a moment. How would we want this to work? Well, we would want to translate the cannon barrel back into the base and then make it come forwards again, giving the effect that it's firing. And as we translate the cannon back and forth, we can see that the Y relative location is changing here. Now, how far back would we want this cannon barrel to go? If we say we want it to come, let's say about this far back, we've got a value of about -24 on the Y there. So in my case, I would want the cannon to go from 0, where it starts, to -24 to make it go all the way back, and then make it go back to 0 again. And we can actually plot this on a timeline with a float track. We would use the float track to drive the relative location of the cannon barrel's mesh. And it would give us the result that the cannon is animating when it fires. So right now I have a challenge for you. Use the blueprints viewport and move your cannon barrel mesh to find your Y relative location range, just like I did a few moments ago. We can use these values to plot a timeline. So the next part of this challenge will be to create a timeline and plot a float track for translating your cannon barrel mesh. So pause here and give this challenge a go, and then in a moment we can continue on animating our cannon. So looking at my cannon barrel mesh, I wanted to start at 0 for its Y relative location, and then I want it to translate back when it fires to about -25 units here, and then translate back to 0 again, giving the effect that it's firing. So I'm going to create a timeline to do this. Inside my event graph, next to my spawn actor node here, I'm just going to right click and scroll all the way down to the bottom and add a timeline. I'm going to call this cannon fire timeline. And inside this timeline, I'm going to create a new float track, and this can be called cannon barrel location. And I need to decide the timeline length. So how fast do I want this whole animation of firing the cannon to be? Well, I want it to go pretty fast, so I'm going to set the timeline length to about 0.8 seconds. Now, I want it to start at 0, so I'm going to add one keyframe, set the time to 0 and the value to 0. And then we want to translate it to about -25 5 units on the Y. So I'm going to plot a new keyframe, and the time is going to be in the middle of our timeline. So that this is going to be 0.4 seconds, and the value is going to be negative 25, and then we want it to come back up again to 0 at the end of the timeline. So 0.8 seconds for the time here, and the value will be 0. And we can use these arrows here to see the whole timeline. We just click on these to fit the timeline vertically here. So this represents our cannon barrel at its starting location and then translating back and then going back to its starting position, giving us the effect that it will be firing. Now let's come back to the event graph and let's grab the cannon barrel from the Components tab. We want to update its relative location. So we're going to drag out the reference that we've just placed on our graph here, and we're going to call the set relative location function. We can split the vector to gain direct access to the Y location value, and we can plug our timeline track straight into this. And then we also want to connect the update from the timeline to the set relative location function. Now we have a problem here when we want to execute and play our timeline, because the spawn actor node that spawns the projectile is looping back to our delay. But we want to play the timeline immediately after our spawn actor node fires, but we also want to retain our looping behavior back to the delay here. And none of the timeline outputs will help us here, because the update output is going to continuously fire, and the finished output only fires when the timeline finishes. We really need an output execution pin for when this timeline starts, and I'm going to challenge you to create this. We've been using a float track up to now on our timelines. However, there's other types of tracks you can create. So your challenge right now is to create a new timeline track that we haven't used yet. I want you to create an event track inside your timeline, and I want you to name the track Cannon Fired. This will create an output execution pin on our timeline. And to make it fire at the start of the timeline, add a single keyframe at 0 seconds. So pause here and create your event track in your timeline, and then come back to the lesson and we can continue on. Okay, so we want to create an event track for our timeline. To do this, we can enter the timeline and we can add an event track by hitting this button in the top left with the exclamation mark on it. So this adds an event track for us. So this event track is going to fire when the timeline starts, and the timeline starts when the cannon fires. So we're going to name this track Cannon Fired. If we come back to the event graph, we can see now that our timeline has an extra execution pin now. However, this execution pin isn't going to fire because we have no keyframes on our track. We want it to fire when the timeline starts. So let's add a single keyframe. We can hold down left shift and left click to add a keyframe, and we can set this time for this keyframe to be 0. And we don't need to really worry about the value here because the execution pin doesn't return any value. So this is meaningless. We can just set this to 0. And this is all we need to do here. Let's come back to the event graph. When our timeline now plays, our cannon fired output execution pin will fire. Okay, we can actually take this and connect it to this reroute node, and we want our spawn actor to execute the timeline. And we want our timeline to play from the beginning every time it's fired. So let's connect this to the play from start, not the play. We want it connected to play from start. We can add another reroute node if we want, just by double clicking on the wire here, just to make it a bit neater. Okay, great. So let's come back to our level and let's hit simulate. And we should see now that our cannons are animating while they fire. We can probably speed up the animation here. So let's come back to the blueprint. Let's come into the timeline. Now let's make our timeline shorter. Let's change the length of it from 0.8 to 0.4. And the middle keyframe here for when we change the location of the barrel, let's make this time 0.2, and we'll make the final keyframe 0.4. So that's going to speed it up for us now. And now if we come back to our level and simulate, we can see that the animation is just a bit quicker for us now. So our cannon is almost there, we have it animating, and we can control the speed of the animation by making adjustments to its timeline. Now the blueprint for the cannon is starting to get a bit more complex, so in the next lesson we're going to tidy it up and we're also going to implement a way for the projectiles to damage the player. So we'll be tackling all of this in the next lesson. Hey and welcome to this lesson which is all about damage functions and events. By the end of this lesson you have learnt how to use Unreal's damage system. You will learn how to implement functions to apply damage to actors and also how to execute events once an actor has been damaged. Okay, so I'm just going to start this lesson off by cleaning up the code for our cannon blueprint before we move on to damaging the player. So looking at the start of our code here, we have the event begin play that connects to a delay. Now, we don't really need to encapsulate this down to a function or anything because it's quite clear what it's doing. It's processing the cannon's fire rate. But there's something else to be said here. Even if we wanted to collapse this down to a function, we actually can't do this because functions cannot contain any latent nodes, basically anything that delays or takes time to complete, and this is why we cannot encapsulate timelines or delays. So let's move on to our spawn actor code here where we spawn our projectile. We can encapsulate all of this into a function. Let's select all the nodes here and right click and collapse it down to a function, and let's name this spawn projectile. Now I'm just going to move the timeline next to it just to make it more tidy here. And now we have this set relative location. It looks like our reroute node is going a bit crazy. Let's just remove all of these out for the time being. We'll clean these up in a second. Now from our timeline we go to this set relative location function for our cannon barrel mesh. So this is updating the cannon barrel's location. Let's right click on this and collapse this down to a function, and let's name this move cannon barrel. And it's not giving us a very good parameter name for our input parameter here. We could just rename this to cannon barrel y location. And now with our cannon fired output on the timeline, we can click and drag this back to the delay here. And we can double click on the wire it creates just to create a simple reroute node there. So that's looking a bit more tidy now and easier to read. So now let's move on to making the projectiles cause damage to the player. Let's close and save our cannon blueprint and let's head over to our projectile blueprint. The only code that we have in our projectile blueprint is this event hit and destroy actor function. Currently when the projectile hits anything, it will remove itself from the game. Now we want to make it so if the projectile hits anything, it will apply damage to whatever it hits and then remove itself from the game. And what we really want out of this is to make it so if our projectiles hit the player, they will cause a damage event to fire on the player pawn blueprint, and then we can use this event to restart the level. Basically just like what happens when the player falls off the map. Now Unreal already has a very powerful damage system with functions and events for dealing with damage. We can call functions to apply damage to actors, and these functions contain parameters for who caused damage and how much damage we want to apply. And we can implement events for when actors receive damage, and these events return how much damage is being applied and also who is causing the damage. So looking at applying damage, there's a few functions we can use and there's many parameters involved for each one. Now our player pawn doesn't have any health. We're not going to need all of these extra parameters on these functions. We just want a very simplified damage system. So we're going to just use the function named apply damage. And even with this function, there's quite a lot of noise with it, but we don't have to use every pin here. Let's just focus on using the damaged actor and base damage pins. So when using this function, we can apply damage to an actor. We have an input pin for who is going to be damaged. And we can decide how much damage we want to apply. And that's all we need to worry about right now. So we can call this apply damage function to cause damage to an actor, but what does this really do? Well, any blueprint actor can implement events for dealing with damage. If an actor is damaged and has this event included on the graph in their blueprint, this event will execute. So we can implement this event any damage into the player pawn to find out when the player has taken any sort of damage. So I've just shown you the functions and events for dealing with damage, And now I'm going to challenge you to implement these yourself. I want you to implement the apply damage function in your projectile blueprint. And with this function, apply damage to the actor that's returned on the event hit. Then inside your player pawn, implement the event any damage anywhere in the player pawn's event graph. So I encourage you to pause here and take your time to explore through the functions and events dealing with damage, and then just give it a go, and in a few moments I'll be taking you through the process. So just pause here for now and then come back when you're ready. Okay, so in our projectile blueprint, we want to call the apply damage function. We can bring up the action menu and we can come down to the game category and we can enter the damage subcategory here. And the first function is the apply damage function that we want to use. So let's grab this function and let's add it between our two nodes here. We can hold down left alt and left click on an execution pin to break it. And we can just move the destroy actor across and insert the apply damage function between these. And let's just hook up the execution pins. Now, who do we want to apply damage to? We have this damaged actor input pin here. Well, the event hit returns the actor that was hit. This is what this other pin is here. We can drag this straight into the damaged actor pin. For right now, I'm not going to worry about any of these additional pins. I'm going to head straight over to my player pawn blueprint. Now let's call the event any damage. We can right click anywhere in our event graph and we can come to the add event and then we can come to game and then damage and then event any damage. So this event will fire anytime this actor is referenced in the apply damage function. So how do we know if this works? Well, let's just use a simple print string now to print out a message saying player pawn damaged. Okay, now let's close this blueprint and then let's just spawn the player here and move in front of one of these projectiles and let's see if we get this print string message up. Okay, so we don't have any message coming up yet, but all the code is correctly implemented apart from one thing on the projectile. We haven't provided a base damage value. If it stays at 0, it means that it's not going to apply any damage at all. So the event any damage will never fire. Let's just put in a value of 1. Now we're not going to use any of these values at all. This is just to make sure that the event fires. Let's close out of this and let's play from here again and let's see what happens now. So we are now getting our print string messages saying that the player has been damaged. So it's important to note that you need to make sure you use a value other than 0 for applying damage. So we have an event for when the player gets damaged. In the next lesson, we're going to use this event to restart the level when the player is damaged. But we also want to avoid any repeating code. So we're going to be tackling all of this in the next lesson. Hey, and welcome to this lesson, which is all about cleaning up blueprint code and looking at different ways we can collapse our code down by using blueprint functions, macros, and collapsed graphs. Okay, so in the previous lesson, we implemented this apply damage function into our projectile class. When our projectile hits the player, it will call this function and apply damage to the player. And what this really means is that it will call this event any damage inside our player pawn blueprint class. Now currently when the player is damaged, it just prints a message to the screen displaying player pawn damaged. But we want it to follow the same behavior as when the player falls off a level and passes through our level restart trigger. We want it to fade out and restart the level when the player is damaged. So what's the best way to do this? Well, just like I said, we're already doing this with our level restart trigger. Let's come into our level restart trigger blueprint. We already have all the code for restarting the level and fading out the camera here. It's just after this branch here. I'm going to select all of these nodes, but I'm not going to copy them. We want to avoid having the same bunch of nodes and code in multiple different places. We really want to avoid copying and pasting our code everywhere. So I'm going to hit Control X to cut the code. And I'm cutting because I don't want to copy it. If we copy it, you are repeating code somewhere. So just always think when you press the copy button or Control C, why are you doing this? Okay, so I'm cutting it. I'm going to come back to my player pawn and I'm going to paste it in after my event any damage here. I'm going to remove my print string And we're going to replace the print string with a do once node. I'm going to hook up the execution pins just here. And we're using a do once here because we only want the player to be damaged once and then execute the fade out and level restart. We want to avoid the opportunity for this to execute multiple times, as it will reset our camera fading and appear quite jarring. So this will help us avoid this. Now if we come back to our level and we play from here, we can see now if we get hit by a projectile, the level fades out and restarts. But if we roll off our level, we can see now nothing actually happens, and this is because our level restart trigger has no code going on other than this check with a branch here. So your challenge right now is to make it so when the player enters the level restart trigger, it will result in the event any damage executing on the player pawn. So pause here to give this a thought and then attempt the challenge, as this will fix our current issue with the level restart trigger. Then once you're ready, come back to the lesson and we can resume. Okay, so when the player overlaps this level restart trigger actor, we want to execute the any damage event on the player pawn. So to do this, we need to apply damage to the player pawn, and we can do this by calling the apply damage function, and we can use the return value on the get player pawn function here as the damaged actor, and we can hook up the true output from the branch to this, and we want to make sure that the damage value is above 0 to make sure that the damage is actually applied to the player pawn. Okay, now let's come back to our level and hit play, and let's roll off our map just here, and we can see that the game fades out and restarts and works as expected. But we can simplify our code here. We can make it so if any actor enters this trigger box, we can apply damage to them. So we can actually remove the branch and this equal check here and the get player pawn function, and we can just use the other actor going straight into the damaged actor here. And look, if we come back and hit play, it works the exact same way but with less code. So whenever the player receives damage at any point, we execute this code that fades the camera out and restarts the level. And this will happen for any other actors that we create that call the apply damage function to damage the player pawn. Now I encourage you at this stage of the course to start exploring in between lessons by creating your own blueprint actors that can cause damage, and make sure to post your results to the Game Dev TV community forum. It'll be really interesting to see what you and other students taking this course can create. Now we want to clean up this code after the damage event in the player pawn here. I want you to try and encapsulate and collapse this down. So your challenge right now is to explore the different options of collapsing your code. Select the nodes after event any damage in your player pawn and right click on them, then try different methods of collapsing your code. So pause here to have a go at this, then come back to the lesson and we can explore this together. Okay, so we want to select all of our nodes after our event any damage, and we want to take a look at collapsing these nodes down. So we can right click on one of the nodes we have selected and we can see the different options for collapsing our code down. Let's start with collapsing it to a function. It's not going to allow us to do this because we have a delay, and functions cannot contain delays. So what else do we have here? Well, we can collapse nodes, and when we do this, it collapses all of our nodes here into a single node, or this is a collapsed graph, so it's kind of like a mini event graph in a way. Now you can see our event graph's actually gone, but we can come back to the event graph just by hovering over event graph here, and we can click it to come back. Now I'm going to undo by hitting Control Z. I'm going to keep doing that till I get my nodes back, and we're going to take a look at the final option, which is collapsing our nodes down into a macro. So it does allow us to do this because macros can contain delays, and when they do contain delays, they have this little symbol on them showing us this clock timer, letting us know that there is a delay inside here. So I'm going to stick with a macro, and macros are reusable when collapse nodes aren't, so that is one thing to keep in mind when using a macro. I'm just going to rename this macro to restart level. Okay, I'm going to hit compile and save, and now let's come back to our level and let's just make sure everything works. Let's start with the cannons. If we play from here and roll into one of the projectiles, we should see that we do restart the level after we get hit, which it does. And then if we roll off again, it should also restart the level, which it does. Okay, but there's a problem here just with our level trigger that we're using, this level restart trigger. It's not really a level restart trigger anymore because it's not restarting the level, it's causing damage to the player. So we're going to rename this just before we move on to the next lesson. This is going to be named BP underscore damage volume. And the folder it's in can also be renamed to volumes. Okay, so that wraps up this lesson. We now know how we can collapse our blueprint code, not only down into functions, but also down into macros and collapsed graphs. In the next lesson, we're going to take a look at creating a win mechanic so players can complete a level and move on to a new level. Hello and welcome to this lesson, which is all about macro libraries. In this lesson, we're going to learn how we can avoid creating the same macro in multiple blueprints by creating macros inside a macro library. Okay, so we're going to start this lesson by creating a volume that we can place anywhere in our level, and we're going to make it so once the player overlaps this volume, we run some code to check to see if the player has collected all the crystals in the level. And if they have, they will complete the level and move on to a new level. So let's create a new actor inside our volumes folder. And let's call this something like BP underscore win volume. You can call yours anything you like. It could be complete level volume or next level volume. But once you've named it, let's open up this actor and let's make it a volume just by adding a box collision component. And we can just call this something like trigger. And we can make the trigger visible at any time by scrolling down on the details panel when we have it selected, and we can uncheck hidden in game. And this is just to help us out for now. You can change this anytime if you don't wish to see it in your level. And this is all the components we need, so let's switch over to the event graph and start coding in some behavior for it. Let's remove the begin play event and also the event tick, so we're just left over with the event actor begin overlap. Now we can check to see if the other actor is equal to the player pawn, and then we can use a branch to get the true and false result from that. But this is all feeling a bit familiar, right? We've already done this inside our crystal blueprint. We have this macro here that's named isPlayer, and inside here we have the exact same code. And remember, we want to avoid any repeating code we may have. Now the issue with this macro is that it exists inside this crystal blueprint, and we cannot use it inside our volume we've just created. But this is annoying, right? This is a pretty simple macro we have here that we would want to reuse many times across our blueprints. And we don't want to have to keep repeating the same code from this macro in every blueprint we create. We always want to avoid repeating code. So how can we avoid this? Well, we can create a macro library. Macro libraries can be used to create common macros, and macros from a macro library can be reused across different blueprints, which is different to creating a macro inside an active blueprint like our crystal, as we cannot use a macro from one blueprint in another because the macro only has scope to its class, meaning we cannot reuse this isPlayer macro inside any other blueprint because it only exists inside the crystal blueprint. This is what I mean when I say it only has scope to its class. But macros from a macro library can be called and used in any actor blueprint. Let's take a look at creating a macro library. Inside our blueprints folder, let's create a new folder called libraries. And inside this folder, we can create a new macro library by right-clicking and coming to the blueprints category here, and we can select blueprint macro library. Now when we do this, it looks like we are creating a new blueprint, which seems a bit confusing, but this is really asking us about the scope of our macro. It says pick parent class here. So as an example, if we chose pawn, we would not be able to call macros from this library inside any actor blueprint. We would only be able to call it inside any blueprints that inherit from the pawn class. But if we chose the actor class, we would be able to call it inside actors and also pawns. And the reason we can call it in pawns as well is because the pawn inherits from the actor class. The pawn is an extended class of an actor. But our crystal and volumes are both actors, so we're just going to select actor here and we can name the macro library. This isn't naming the macro, this is naming the library which can contain numerous macros. I'm just going to call mine cc for crystal cavern underscore macro library. And we can double click the library to open it. And when we do this, it creates a new macro for us straight away. We can see this in the My Blueprint tab, which is in the top right inside this interface. And you can see here it's asking us a name for our macro. We can call it isPlayer. And we can add more macros here by hitting this new macro button, and we can delete them by selecting them and hitting the delete key. So this is how we add new macros. And on the details panel, we can add inputs and outputs just like a regular macro, and we can even start coding inside the blueprint graph, just like it's a regular blueprint. So your challenge right now is to take a look at your isPlayer macro from your crystal blueprint. Then create the same macro in your macro library. And once you've done this, remove the old isPlayer macro from the crystal blueprint and delete it from the My Blueprint tab. Then try searching for the new macro from your macro library and add it to the event graph to replace it. So pause here to attempt this challenge, and then once you're ready, I'll walk you through the process in a few moments. Okay, so inside our crystal blueprint, we have this isPlayer macro. I've recreated this macro inside my macro library. But notice how inside the crystal blueprint, the input execution pin doesn't actually have a name, but inside the macro library, my macro does have a name and it's named new parameter. Now I can't actually remove this name. It says the name cannot be empty. So how do we remove the name on the execution pin? Well, you just need to name the pin execute, and the engine will read that and remove the name for you visually on there. I've also put my macro inside a category named Crystal Cavern Macros. So inside my crystal blueprint, I'm going to come back to the event graph. I'm going to remove this isPlayer macro and delete it from the My Blueprint tab. And I'm going to right click and scroll down to the new Crystal Cavern Macros section and call the new isPlayer macro. If you don't see a macro in your category that you've created, just make sure to save the macro library because it needs to be saved in order to apply the macro to its new category. Okay, now we can just hook this up with all the pins just like it was before. And one thing to note here is if you double click on the macro, it will take you to the macro in the macro library, and you can select the macro and you can even change the color of the macro so it looks different in the blueprint editor here. But just be careful with the colors here, not to confuse them with any other functions inside the engine. So we're now using our new isPlayer macro, and the cool thing here is that we can reuse this inside another blueprint. We can remove the code from our win volume blueprint that we started creating at the beginning of this lesson, and we can now call the same macro. Okay, so that wraps up this lesson. In the next lesson, we're going to take a look at how we can get all the crystals that exist in the level to see if the player has collected them all. So when you're ready, I'll see you in the next lesson. Hello and welcome to this lesson, which is all about getting actors of a particular class. In this lesson, we're going to learn how we can get all the actors of a particular class that exists in a level, and we're going to learn all about arrays and how we can call functions on them. Okay, so in the previous lesson, we started coding this win level volume that we'll use as a trigger point for completing our level. When the player enters it, we want it to run some code that checks if there's any crystals remaining in our level. And if no crystals remain, the game will load the next level. Now, how do we check to see if we have collected all the crystals in our level? Well, if we right-click to call the blueprint action menu in the event graph here, we can scroll all the way down to the utility section, and in the utility section, if we keep scrolling down, we can find some functions called get all actors, and there's different results here. We can get all actors of class here, and it says this is a slow operation, use with caution and do not call it every frame. Okay, and the reason it's telling us that is because when this function is called, by default, it's going to return every single actor in your level. So you can imagine it could be quite heavy. But we can use this actor class here and filter just for the actors that we want to search for. For example, if we only want to return all of our crystals in the level, we can drop this down and just filter by the crystal blueprint. But look how it returns our crystals. There's this strange pin here that we haven't seen yet. And this is an array. It's returning an array of all our crystal actors. An array is a collection of elements of the same type, and each array element has an index. And the first element of an array starts at index 0. Let's visualize this a bit by taking a look at some of our crystals. All these crystals here are of the same type. They are this BP crystal class. Now let's imagine these crystals are in an array. An array is a collection of elements of the same type, and each crystal here is an array element. And we have 5 elements in our array here. There's 5 crystals. And each array element has an index. And the first element of an array has an index of 0, not 1. So it's important to note that your first element of your array doesn't have an index of 1. It's always 0. So in blueprints, arrays are symbolized by these dotted squares, and with arrays and blueprints, we can call functions on them to alter them or find more information out about them. We can find array functions in the blueprint action menu, under utilities, and then under the array category. There's lots of functions to call here, and I won't be covering every single one, but one function here is the length function, and the length function returns how many elements are in your array. So if we get all the actors of our crystal blueprint class and call the length function, it will return how many crystals are in our level. So your challenge right now is to get all your crystal actors and get the length of the array that's returned, and then with the length value, check to see if it's above 0. So we call this getAllActorsOfClass function, and we filter the results by searching for our crystal blueprint. And this will return an array here that contains all of our crystal actors that exist in our level at the moment that this function executes. So with the return value, we can drag it out and we can call functions on it by coming to the utilities category and then the array category. And we can find out what each function does here just by hovering over it, and it gives us some more information. Now we want to call the length function. This returns how many elements are in the array. So in our case, it's going to tell us how many crystals are in our level. And we can check to see if there's more than 0 crystals in the level. And to do this, we can drag out the return value of the length and we can put in the greater than symbol to get an integer greater than integer here. Okay, so we're asking a question here. We're asking, is there any crystals remaining in our level? So with all these nodes selected, we can actually encapsulate this down into a function called any crystals remaining. Now you may have noticed this function is color-coded blue. If, for example, we get a getActorLocation function, notice how it's green, okay? And if we right-click and use the action menu here and just type in array and take a look at any functions here, we can see that sometimes they're color-coded green and sometimes they're color-coded blue. So this is actually a symbol for something here. So we're going to move straight into the next lesson and learn all about this and how this affects our functions and our blueprints. So when you're ready, I'll see you in the next lesson. Hello and welcome to this lesson, which is all about pure and impure functions. In this lesson, we're going to learn about the difference between these functions, and we're also going to learn about pure const functions. Okay, so in the previous lesson, we set up some code in our win volume to tell us if there are any crystals remaining in our level, and we encapsulated this into a function named anyCrystalsRemaining. But this function isn't returning a result for us. But before we get to that, I want to point out that this function here is an impure function. Blueprint functions can be pure or impure, and we've been using pure and impure functions throughout this course. Impure functions are color-coded blue. And one thing to notice here is that impure functions have execution pins on them, when pure functions do not have any execution pins. And impure functions can affect state. Now, what do I mean here when I say they can affect state? Well, I mean affecting the state of the actor they are called on, or affecting other actors or objects that exist in the game world. Using the setActorLocation function is an example of affecting state, as this function changes the location of an actor in the world. Therefore, it's changed the state of the actor, and setting variables in blueprints is also another example of affecting state. So impure functions can affect state. Now, pure functions, on the other hand, are color-coded green, and they are generally used for calculations and returning data. One way to think about pure functions is that you ask a question and you get an answer. And pure functions have no execution pins, and your first response might be, well, how or when do pure functions run? Well, pure functions run whenever any of their return values are used in your code. And the most important bit of info to take away here is that pure functions promise never to affect state, meaning they promise never to affect the member variables or the state of the actor on which the pure function is called, or any other actor or object in the game world. This is also stated here in the function section of the Unreal Engine 4 documentation. It says functions can either be pure or impure, and the main difference is that pure functions promise not to modify state or the members of the class in any way, while impure functions are free to modify state. But here's the twist here: even though pure functions promise never to affect state, they still can affect state, and this isn't mentioned here in the documentation. But we can enforce this promise. In order for a pure function to never be able to affect state, you want to mark the pure function as const to make it a pure const function, which enforces that this promise of protecting member variables and state will never be broken. We can change if functions are pure or pure const via the details panel when we are inside the function or when we have the function selected on the event graph. So your challenge right now is to mark your any crystals remaining function as pure, and then mark the function as const to make it a const pure function. Marking the function as const might be a bit trickier to find, but I promise you it's there, so try digging around to find it. And the final step of this challenge is just to make sure to return the Boolean result on your function. So pause here to attempt this challenge, and then once you're ready, we can go through this together. So when we select our any crystals remaining function, which is an impure function, we can make it pure by checking the box on the details panel, which is just pure. So we now make this a pure function when we check this box. And we can see that the function changes entirely. It removes all of its execution pins, so it's no longer in the execution flow here. And there's no pins at all on this pure function. We can enter the function by double-clicking on it, and we can view our code, and we want this function to return this Boolean result here. So we can't see any details about the function on the details panel because we don't have the function selected. So if we just select the function, or if we select the entry node here, it will bring up the details. Now, we want to add an output. If we add a new parameter for the output here, it will add this return node onto the graph for us. We want to make sure that we hook up all the execution pins in here to make sure that our function fully executes, and we can hook up this Boolean value to the parameter. But there's something I want to show you here. If we remove the output values, the return node still stays, and we can create output pins on this return node just by dragging and dropping pins onto the node, and that adds a new return value for us. Okay, if we come back to the event graph, we can see that our pure function now has a return value on it. And the pin is actually named return value as well, which is fine. We can think of this pure function as asking a question. The function name is the question, and the return value gives us the answer. So this is a pure function, and Unreal tells us that pure functions promise never to affect members or state of the class, meaning if we create a variable now, and just throw it into this function and try set it, Unreal tells us that we shouldn't be able to do this. Okay, if we hit compile, it should give us an error, and we can see it doesn't give us an error. We shouldn't be able to call functions like setActorLocation, which is clearly changing the state of an actor somewhere in the game. Okay, and if we compile, Unreal still doesn't care about this. This is because this function is not a pure const function. If we select the function again, and on the details panel, we can expand this little white arrow where it says show advanced, and we can check this const box to make it a pure const function, and we can see that listed just on the top here as well. And now if we compile, Unreal starts throwing errors at us, telling us that we cannot compile this blueprint because these functions and variables are changing state. Okay, we can remove these because I'm just using these as an example, and if we hook this up and hit compile, we see we have no problem now, because this function, as it stands and exactly how we want it to stand, it does not affect state. So this is perfectly okay for us, and this is what we want for pure functions. We never want pure functions to affect the state of a class. Now I'm just going to switch back to my event graph, and we can test this out just by using a branch here with our function. So something overlaps our win volume. If it's the player, are there any crystals remaining? If there are, we can test just by printing a string and saying crystals still remaining. And if there's no crystals remaining, we can just print that message. So let's hit compile and save. I'm just going to test this by making sure I've got my win volume in my level. And I'm also going to just remove the crystals that are far away from the start of the level, just so I can easily test this here. I'm just going to hit play and enter my volume, and we can see it prints a message saying that there's crystals still remaining. Now let's put this to the test. Let's collect all our crystals here and roll back into this. And what does it say? It tells us that there's no crystals remaining. Okay, great. So the next step for this is to make it so if we do collect all our crystals and enter the volume, the game will load a new level. So that's just what we're going to be tackling in the next lesson. Hello and welcome to this lesson, which is all about working with arrays. In this lesson, we are going to learn how we can arrange all the names of our levels into an array, and then we're going to start creating pure and impure functions that we can use to retrieve information out of the array, which we can then use for loading new levels once a level has been completed. Okay, so we're going to be making use of what we've learned in the previous two lessons by working with pure and impure functions, and also by working with arrays in this lesson. Inside our win level volume, we're going to start by creating a new function called complete level. And in our event graph, we can remove the print strings that we created in the previous lesson, and we can remove this variable that I left over from the previous lesson as well. We're going to drag out the complete level function onto our graph, and we're going to hook it up to the false output of the branch. When no crystals are remaining, we're going to execute this complete level function. And this function is going to handle loading new levels for us. And to help us do this, we're going to create an array that is going to contain the names and order of all the levels in our game. To create an array, we're first going to create a new variable, and we're going to call this level names. And we're going to change the variable type from a boolean to a name. Now when we hit compile, we can see on the default values that we can assign a value to the name here. We want to provide numerous level names, so we want this to be an array. To change this variable to an array, just where we selected name, we can see this line symbol just next to it, and we can click this and select the dotted square here, which represents an array. And now this is an array. It still looks the same here, but if we hit compile, it now updates the default values to an array. It's telling us that there's 0 array elements, but we can add array elements by hitting this plus icon just next to it. And this is where we can provide numerous values now to this variable. And this trash can icon just next to it removes all the array elements. So we have only got one level now, but let's just imagine for the time being that our level name array has 2 elements. The array here is going to contain the names of all our levels, and the order of the array is going to represent the order in which our levels will be completed and loaded. When we complete level 1, it's going to load level 2, and so on. So let's take a look at setting up this array to represent the first 2 levels of our game. We can add 2 elements to it by hitting the plus icon twice. And the first element here is going to be the name of my first level, which is the current level I'm in. And we can see the name of the current level just by looking in the viewport, and we can see it in the bottom right corner of the viewport. So it's level 1 for me. So the first level for me is level 1. And I want the second level to be level 2, but I don't have a level 2 currently. So for right now, I'm just going to do a file save current as to save the second level as level 2. And now we have 2 levels for our array here. So this is all I'm going to do with the array. We can come inside the complete level function to start implementing some code for it. Now what do we want to do with this complete level function? Well, when it executes, we want the engine to load the next level, but we need to be careful here because we need to ask some questions first. We need to know if the current level is the final level in our game. And to be able to ask this, we need to know the index of the current level in our level names array. And with this, we can also ask what is the next level to load. So we're going to start mapping out these questions as pure functions. Now let's start by creating a pure const function for getting the index of the current level. Inside this function, we want to get the current level name. Then with our level name array, we are going to call the find function to try find the current level name in our array. And the find function returns an integer. It will return the index of the current level. And we will use this index as a return value on our pure const function. So your challenge right now is to have a go at setting this up. Create a pure const function called getCurrentLevelIndex. Then inside this function, call the find function on the level name array to find the index of the current level name. Then make the pure const function return this index. So I encourage you to pause here to have a go at this challenge, and then in a few moments we can walk through this together. Okay, so let's add in a new function called getCurrentLevelIndex. And we want to make this function a pure const function. So we'll check the boxes for pure and for const. Now with this function, we want to get the current level name. And we're going to hook this up with the execution pin here. And then with our array, we can call the find function, or the find item function here. And we can chuck our current level name into the input for this. And it converts it from a string to a name. So it's going to look through our level names array and try find our current level name there. And it will return the index of it. And we want this to be returned on our function. So to do this, we can select the entry node or select the function on the My Blueprint tab, and we can add in a new output called return value, and we can drop down from Boolean here and change it to an integer. And let's just hook up the execution pin to this and make sure the find output is connected to the return value. And now we can hit compile, and we can come back to the complete level function, and we can now drag out our newly created pure const function called getCurrentLevelIndex. So let's just visualize briefly what this is really doing. Imagine we have 4 levels in our game, and we have all the names of them in an array. To get the current level index, we provide a name, and then the engine searches through our array and matches the array element with the same value that we provide. So here, if our current level name is level 3, the find function searches through our array and tries to find a match with an array element that has a value equal to level 3. But remember, our function returns the index of this array element, so the index it will return here will be 2. Okay, so we can get the index of the current level name. Now how does this help us here? Well, let's look back at our questions. We can now ask how to get the current level index from the level array, which now allows us to ask the first question, which is the current level the final level for our game? Let's grab our level names array and let's call a function on it by coming to utilities and then array, and let's grab the last index function. This gives us the index of the final level in our game. We can drag this out and we can use the equal symbol to grab an equal integer, and we can compare this to the index of the current level. So this code here now asks the question, is the current level the final level? And it returns a true or false result for that. We can select all of this and we can right click and collapse this to a function called isFinalLevel. Now we want to make this a pure const function, and we want to add an output for this named return value, and we can make this a boolean. And if we just double click on the function to enter it, we want to make sure that our code sits nicely into this and then returns our boolean value here. So now when complete level is executed, we can ask if we are playing the final level in the game, and we can use a branch with this and connect the return value to the condition here. Now if it isn't the final level in the game, we want to load the next level. So our next question is going to be, what is the next level to load? And I want you to have a go at this one. Create an impure function called loadNextLevel. Inside this function, get the index of the current level. And remember, we already created a function for this, so you won't have to write any code to do this. So call the function we created, but increase the index by adding the value of 1 to the result. This will give us the index of the next level in the array. And then the final step here is to get an element from your level names array by calling the getArray function. And then we can use the index we just calculated to get the next level. So pause here for this final challenge, and then when you're ready, we can wrap up this lesson. Okay, so let's create a new function called loadNextLevel. And inside our complete level function, we can call the loadNextLevel function from the false output of the branch. So when complete level is executed from the event graph here, we check to see if we are on the final level of the game, and if we're not on the final level of the game, that means that there's more levels to play, so we then execute the loadNextLevel function. Now we want to get to the index of the current level. We've already created a function for this, so we can drag it from the function tab here onto the graph. Now this returns the index of the current level, but we want to add 1 to this to get the index of the next level. So we can drag out the return value, we can put in a plus symbol to get an integer plus integer node, and this is now the index of the next level in the array. So if we grab our level names array and use a get, and if we drag out the array pin and just type in get into the search bar, we can get 2 array functions here. We can get it by using an index, which is the a copy version here, or we can get it by using a reference. We're going to use the get a copy version just here. So we can plug the return value of our plus node here into this, and this is basically saying look at our level name array and gets the current level index and add 1 to it to get the next level name out of the array. Now what can we do with this? Well, we can call the open level function, and we can use the result of our little calculation here as the level name to open. Okay, we can hook up the execution pin here. So we can clean up our code even further here just by selecting all these nodes, and we can right click on them and collapse them down to a function, and this can be called getNextLevelName. And this can be a pure const function. And if we want to change the output pin name, we can change it to something like return a value. Now let's come back to our event graph and let's view our blueprint from the top level. I'm also going to close all my tabs here, so I just have the event graph. So looking at our blueprint from the top level, when something overlaps with our trigger volume here, we check to see if it's the player. And if it is the player, we check to see if there's any crystals remaining in our level. If there are crystals remaining in our level, we don't do anything. This means that the player hasn't collected all the crystals. So once the player does collect all the crystals and overlaps with this volume again, this would mean that the false output would fire. So when no crystals remain, we execute this complete level function. And this function checks to see if we are on the final level of our game. And if we're not, we load the next level. However, if we are on the final level of the game, what do we want to do? Well, this is totally up to you. We could reopen the first level of the game by getting the first element of our level names array, and we could just open that level. And at that point, our game would loop once you complete the final level of the game. Or we could just call the quit game function to exit the game once all the levels have been completed. So it's totally up to you, and make sure to post your results on the Game Dev TV community forum. But in my game, once the player has completed all the levels, I'm just going to call quit game. So before we end this lesson, we want to just organize our functions here. I'm going to select the complete level function, and I'm going to put it in a category called level management. And when we hit enter here, we can see on the My Blueprint tab where we have the function section, our complete level is now in this level management category. And we can take these other functions that we've created that relate to level management, and we can click and drag and drop them into this level management category just to keep them organized. And now when we hit compile, we can right click in the graph to bring up the action menu, and if we scroll down we can find our level management category with our functions inside of it. Okay, great. So now remember, when you create and save new levels for your games, you can add the names of your levels to this level names array that exists in this actor, and you can add them in the order you want the levels to be played. So when the player completes levels, the player can then move on to a new level. Okay, so that wraps up this lesson. We're now ready to start wrapping up our game by creating some levels with all the assets we've created, and we can also review our code before packaging the game. But before moving on to the next lesson, I'm just going to leave you with these slides here that show the functions and the codes we've implemented for them in this lesson. But once you're ready, I'll see you in the next lesson. Hey, and well done for making it this far. In this lesson, we're going to be finishing up Crystal Cavern by taking a look at casting, and we're also going to be fixing some issues with the physics of the player. And we're also going to spend some time designing some levels. Okay, so in our project, we now have a bunch of actors that we have created all throughout this section. There's so many more actors we could build to continue extending our game, but that's going to be a long-lasting challenge to you as a student of this course. What other actors can you build with what you've learnt from this section? Make sure to post and showcase your work on the Game Dev TV community forum so us, instructors, and other students can see your results. Now I currently only have 2 levels in my game, but I really only have 1 because my second level is just a duplicate of my first level. My first level is really not designed out yet either, so in a moment I'm going to spend some time designing my first level better, and then I'm also going to design a completely different second level, and I want you to do the same if you haven't done so already. Design at least 2 levels by making use of the BSP geometry tools, and make use of all the blueprint actors we have built in this section to build out your levels. I encourage you to have a go at this challenge and then continue the lesson to see how I have designed my levels, as I'm going to do something quite interesting in my second level. So pause here and make use of all the actors and the BSP tools we've been using in this section to create some levels, and then when you're ready, come back and resume the lesson. Okay, so here is my updated level 1. I've changed the materials of the BSP geometry in my level, and I've also tweaked the lighting. With the player pawn class, I've applied a material to the mesh, and I've increased the acceleration multiplier to give the player some more control, and it also feels a little more fast-paced while playing. In my bridge path areas here, I've added a spotlight above with a very soft intensity just to help the player see a little better. I still have my cannons in the level that the player has to avoid, but later on in my level, I've added some pipes that I've just made with additive and subtractive cylinder BSP brushes. At the end of my level here, I've placed a wind volume inside this final pipe. But we need to remember that the player has to collect all the crystals before moving on to the next level. So something to keep in mind is to allow the player to return to previous areas to collect any crystals they may have missed. Once the player has collected all the crystals and enters this pipe in my level, it loads the next level. Now here's the interesting thing here. In my second level, it looks like it's completely changed perspective a bit. And it has, because when this level loads, the player's spring arm has adjusted its pitch and its distance to give us this different perspective. So I'm going to show you how I've done this now, just as an option for you, as it's pretty easy to do. Inside my player pawn, I'm going to create a new function called adjust spring arm. And I'm going to add two inputs into this function, and they're going to be a float input type. The first parameter name is going to be distance, and the second parameter name is going to be pitch. We're going to use the distance input parameter to change the target arm length of the spring arm, and we're going to use the pitch input parameter to set the world rotation of the spring arm. So to do this, we can grab these spring arm components from the components list, and we can click and drag it onto the graph. To change the spring arm's distance, we can call set target arm length. And we can simply plug our distance input parameter straight into this. And let's make sure to hook up the execution pin here. Now for the pitch, to change the pitch of the spring arm, we want to change the world rotation of the spring arm. So we're going to drag out the spring arm reference again, and then just call the set world rotation function. So this takes in a rotator. We can use a make rotator to gain access to the roll, pitch, and yaw values here, or we can just right click on the pin to split it to gain access to the roll, pitch, and yaw. We can just plug the pitch straight into it. So this is all we need to do here for this adjust spring arm function. We can hit compile, and if we come back to the event graph, we can drag out the function just to take a look at what it looks like. So we just have some simple input parameters for the distance and the pitch to adjust the spring arm. And we don't want to call this inside the player pawn because we might have many different levels, and we don't want this to be applied to every level. And currently I'm only changing my camera's properties or adjusting the spring arm on level 2. So this is where we can bring in the level blueprint again. We can do something very specific in level 2 by using the level blueprint. On begin play in level 2, we can get to the player pawn and we can call our new function that we just created. Now let's take a look at what happens here when we drag out the return value and try to call our adjust spring arm function. We can see that we have no results for the function even though we just created it. This is because the return value doesn't actually return our custom BP player pawn blueprint class that we created at the start of this section. Let's break this down quickly. In Unreal Engine 4, when you create a pawn class, you are inheriting from Unreal's parent pawn class. You are taking Unreal's parent pawn and you are extending the class by creating a child of it. So this return value on the getPlayerPawn function is actually returning Unreal's parent pawn class, not our custom class, which is why we cannot access our function. But we can do this by casting. Casting allows us to access the properties and functions of the class that we cast to. So when I drag out the return value here and type in cast, I'm trying to ask what type of pawn class am I working with here. So if I choose cast to BP player pawn and hook this up to the begin play, we're saying get the player pawn, is it the BP player pawn blueprint class? If it is, this output here will execute, the one with no name. This is the true output, so this will fire. If it's not the player pawn, so for example in our game mode if we were set to the default pawn, the cast failed would fire here. And then we have this as BP player pawn reference pin here. So this is a reference to our player pawn class. If we drag this out, we can now call our adjust spring arm function. And we can change the distance here. So I'm going to change the distance of the spring arm to about 850 units, and then the pitch can be negative 15 units here as well. So when we start the game, or start level 2, mind you, when we start level 2, we get to the player pawn, we check to see if it's the BP player pawn class, and if it is, we adjust the spring arm with these new values. So now if we come back to our level and hit play, we can see that the perspective has changed and it's only applied to this level because this code is only executed in the level blueprint of level 2. Okay, so before wrapping up this section and packaging our project, there's one more issue I've noticed that we should tackle. I've noticed that the player pawn sometimes spins endlessly when moving around the level. And this is because there is no damping applied to the mesh of our player pawn. Damping only affects components that are simulating physics, and we can think of damping as a resistance against moving or rotating. There's two different types of damping. There is linear damping, and we can think of this as how much resistance against movements we want to apply. And then there's angular damping, and we can think of this as a resistance to rotation. So a quick challenge for you right now is to apply damping to your player pawn's mesh component to prevent this endless spinning from happening. So pause here and go take a look at your player pawn's mesh component, and then we can move on to packaging our project. So to prevent this endless spinning, we can come to our player pawn blueprint, we can select our mesh component, and where we check simulate physics, just under this, we see the linear damping and the angular damping values here. Now we want to prevent the endless spinning, so we're thinking in the terms of rotation here. So let's just apply a higher value to this angular damping. I'm just going to use the value of 0.8. But you need to be aware that this is like a drag that's going to be applied against your mesh to slow your rotation down. So make sure to tweak this while tweaking your acceleration multiplier in your player pawn. But this will prevent the endless spinning that we see. So just keep tweaking those values there. Okay, awesome. So we've covered quite a lot in this section. We've covered how to create blueprint actors and pawns. We've covered how to create blueprint variables and also how to expose them. We've learned about controllers and possession, how to apply damage to actors, and how to create timelines and timeline tracks. And we've learned the difference between pure const, and impure functions, and we've also learnt how to create macros and macro libraries. And we've done a lot more too, and I really hope you've enjoyed this section and that you feel like you're starting to harness the power of blueprints. And again, I encourage you to post and showcase your work from this section to the Game Dev TV community forum. And if you have any questions, please post there too, as myself or other students can reply and help out. So I'm going to leave you with this final challenge for this section, and it's all down to you. I want you to package your game. Only include the maps you are using in your game, and we've covered this in section 1. You're going to be looking inside your project settings to do this. And this time, try packaging a shipping build. So well done for making it this far, and just keep at it, keep blueprinting, and see what else you can do to extend Crystal Cavern.